muted. I'm back. All right, there we go. Oh, what's that doing there? I had to move the monitor for a LAN party, so everything got shuffled. Okay, I think I'm alive. I'm ready to go. There's been some stuff going on external to me. People in bad shape that are, family, friends, and so I may get called away. I'm not sure if I will. Probably we're going to be okay to stream. But I am on call, so I've got to pay attention to my phone even more today than I normally do, which I hate doing. Don't like doing it, but, gotta do what you gotta do. Oh, bother stream detected. Yes. Yes, welcome. Welcome. We've got cool stuff to work on today. It's all op amps. Let me just refresh to see how, let's see. So we know Twitch works. I need to pop out YouTube. Let's pop out YouTube. Pop that shit out. Should we get YouTube chat up here? Pop out. I need to do my uploads again. I need to get back rolling into that. I'm not quite done taking a break from it, but I will get the uploads, that last 100 uploads done. YouTube sent me an email like, re-engage with your audience by posting something on this. And I'm like, no, I'm not going to do that. Because I'm still, these streams, these live streams are still uploading to that channel. So I think that should count as engagement. Make my OBS window big again. Okay. Close the barn door on that one. How's it going, everybody? I've been working on the module tester module, and I have managed to get 6 channels of output. 6! Oh, I should turn on the scope. That'd be helpful. 6 output channels. Can you believe it? Which means that all 6 of the plugs on the front of this module that we're building are going to be able to output audio, full audio. Since the Teensy 4 is such a fucking bruiser, it should be able to handle all the outputs and all the inputs that we could ever throw at it. Probably and then some, but we don't need and then some. I think 6 channels is plenty. 8 channels would probably be achievable. In order to get that last 2, you have to run, and it's not really for the last 2. Unfortunately, channel B, because it's like output A, B, it's A, B, C, D, right? A, C, and D are accessible via the output pins. Channel B, you have to solder to one of the pads under the board. So this is actually I2S channel B. So technically, I am utilizing 8 channels of I2S, but I am unable to reach 2 of them. I don't really need 8 channels. We only have 6 plugs on the outside of this thing, and I don't want to be bogged down making this project until I'm dead. Basically, all of our trigger signals, our control voltages, any output that we are capable of making is going to be done by these 3 elements right here, and it's all accessible in the Teensy 4, or rather the Teensy audio tools. They are super duper powerful. We're going to be able to do our analyses using those audio tools as well. We'll see when the Teensy 4 actually gets bogged down. I'm sure everybody already knows, because you can probably look it up, right? Somebody's going to look up, I did the Teensy 4 audio explosion test and I was able to fit this many dicks into it. But like, I'm not that person. I'm not going to look that up, because it's more fun that we actually do stuff instead of just putting everything down on paper. Because, like, people are freaks. They've already done all the analysis of the Teensy 4 and what it's capable of. So it's probably a known quantity, but we're going to do it in context of our project. So we're going to build a bunch of op-amp circuits right here, and then we're going to build more op-amp circuits up here. Some of them are going to be 3 volts. Actually, maybe we should build them down here. This is my plus minus 12 work area right here. So this is plus 12, minus 12. But then I don't know, maybe down here I'll make a 3 volt working area, because 3 volts comes right over here, so we could just skip it down into, or we could skip it over into the rail. Oh no, we can't. We're using this rail. So maybe we skip 3 volts down here, and then we hopscotch it over to a bunch of op amps in this area. We'll have to figure this out. It'll be a little bit of a growing pain, I guess. I do have an I2C ADC. I don't think that's actually going to be useful. And then I also have an I2S DAC. And the thing is, we can still receive channels with this. There's another I2S line or we could, well, no, if we declare the hex output, all of A, B, C, and D are being used as data out. But we can make this into data in and put it into the other I2S channel. I don't think we need to do that, though. And this thing only has, what does it have? It has like 2 channel input. RN and LN, yeah, this is only 2 channels. So, ECK output, left-right clock, and then serial clock, ground and 3 volts. And then these are the other side, I think there's control channels. So I don't think we're going to be using this. We're going to go directly into the Arduino, which are the analog inputs on this side. I think we do have 6. I'm not totally certain we have all of them when we consider that eventually I am going to be using a level shifted screen that's on serial. Serial's over here. And then a port expander on I2C. May have to use alternative I2C channels to get the port expander working. This is all a stress test, right? We just build up our physical functionality until it all works, and we know that it all works in conjunction with each other, and then we can build out functions of that, and then from there, those functions can be called upon by a UI, and the UI element is everything that the screen involves. I've been working with the screen a little bit. I'm still a little bit flustered on it. We got the screen working with an older Arduino and AI. Where did it go? Oh, it's right here. We got this working with an older Arduino and AI, but I need to get it working on the Teensy 4 serial, so I'm just gonna have to like sit down and look it up. You know, it shouldn't be too hard to do. And then I've got stuff from Nurataki that's gonna help me design the screen, I think, because it's not just a character screen. It's not just a character screen. It's not just an image screen. It's a hybrid of both. And I think it's a little bit clunky how it displays images. So I don't know what kind of image display we're going to be capable of doing on it. This program's, look at this thing. This is I called it Windows 3.1, but it's really a Windows like 98 kind of screen. Craziness. I should probably clear the chat. I don't know how to do that. Hey, what's up? Nothing's working. So yeah, we got some stuff ahead of us. The I2C port expander is going to be for buttons and everything. Yeah, this is a very Japanese UI. It's very, very busy. This is what I was talking about with engineering UIs. At least they gave us like some different colors on things so that we can sort of detect a grouping of functionality. But other than that, I mean, the size is tiny and everything is just so busy. So busy. What this will look for is a, not FTDI, but just a COM port. It'll look for a COM port, and then we can plug the screen into the COM port, and this lets you kind of like design and work with the screen a little bit in their way. I don't know if I'm going to end up using anything from this program, but it'll at least get me a little bit familiar with how the screen works and, you know, how to make ASCII font download stuff. But that's not what we're working on today, because this scares me. Windows 95 and Japanese clutter design. Yeah, there you go. They still design UIs like this. Have you seen EDF 6? It's the most busy, it's like a maximalist UI. It's insane. It's like a migraine headache. Craziness, craziness. Fallout London looks really fun. I've been watching a couple streamers playing Fallout London, and it does just look like as if Bethesda made a Fallout game in London. They did that good of a job putting together this free mod. My only problem with it is that I probably have to do a unique install of Fallout 4, and I just finished modding so much into Fallout 4, and then I stopped playing. I wanted to do a little bit more of the plot of the game, but I never got around to it, because every single time I play Fallout 4, I end up deep in the building mechanic. The building mechanic is like crack. I cannot drop it. And then I burn out on the game. Happy Tuesday, make mistakes. How you doing? How you doing? Welcome to Tuesday. I don't have a lot going on. I've just been taking care of the dog and then putting out family fires. There's some stuff going on right now that I don't really want to fully share, but I've had my attention span split on all that. I basically am taking care of everybody here while this stuff goes down. Yeah, life happens. If it gets in the way of stream, I'll try to give you guys a vague title, but it's nothing involving me directly. It's stuff that, you know, like, I support the people in my life kind of thing, you know? Right, let's get these out of the way. Fallout 4 mod, got excited, thought they released a new game. No. There would be so much more buzz for that. No. It's the mod team behind Fallout London, and they have done an amazing job making a unique setting for Fallout 4. It's almost like a complete expansion. It's not an overhaul, because everything still kind of looks like New England. I know it's New England versus England, but still, everything still kind of feels like New England. But they made entirely new environments, and some newish mechanics, and kind of rolled back the wall of perks and stuff. They did some really good stuff. Is it like New California or New Vegas? Not really, no, because that's just desert. It's like, it feels like old New England. It's like, I'm not familiar with London. Maybe that's part of it. Like, I know a little bit of New England. I know a little bit of Boston. But looking at the environments and stuff, it's still Fallout 4. Like, there's very much asset sharing, and it still has that feel, but it's supposed to be London. I think it does a good job. I've heard it's a bit buggy, so OG, yeah, it could be an OG Bethesda release as such. Yeah, you have to run, what is it called? There's something you have to run, like, you have to downgrade your copy of Fallout 4, and then you have to run, what do you call it? There's a tool to help crashing, and then it's playable, decently playable, actually. Not totally bug-free, but that's mods for you, especially something so immersive and not immersive, so complete. You know, complete overhaul. What is this song? What is going on with this song? No, you're getting skipped. Stupid meandering stuff. 6 channels of audio coming out of this thing right now. Pretty cool. And this thing is not even breaking a sweat. It's not even close to being utilized at its full potential. I don't even think this whole device will utilize this thing at its full potential. This thing can be overclocked to a gigahertz. I used to have a processor that could do a gigahertz, and it was a big deal back in, what, 1998? I think it was a Celeron? I forget. Crazy town. I don't know what the devs are going to do. I'm not sure. Right now, I guess they're just hyping the game release. But are they going to then go and do some bug fixes and stuff? Because I guess it certainly could use that. The fact that it functions at all is a miracle. They spent a long time working on it, and I guess right now it's working on the good old games version of Fallout 4. So the GOG version is required in order to install the mod, and then, yeah, you got to use the downgrader. Be analog, or is it? It's input from ADC, and then I'd have to run that into analysis. What's all that? A2 is used for audio input. This circuitry is recommended. Wait a minute. Are we gonna have trouble running? We might. Man, I might need a DAC that has enough channels. Yeah, I have the Steam version too, so I'm not sure what would happen there. I'd probably like to use so much less power to do so. Can we do audio analysis from other channels? Because the first they lead with pin A2 is used for audio input. The circuitry is recommended. Jeez, they're doing a lot of stuff over here with 3 volts and ground. I mean, that just might be general audio input. We have a plus minus, or sorry, 0 to 3.3 volts. Signal range is 0 to 1.2. Control voltage from plus minus 5 can be adapted with a simple circuit or better op-amp based circuitry to TNC 0 to 1.2 volt analog input. So we have to scale all these to 0 to 1.2? That ain't right. Wait a minute. both access the hardware at the same moment, analog read can end up waiting forever, which effectively crashes your program. Analog read can be used on Teensy 4.x while audio input analog is running, as long as pins 26, 27, 38, and 39 are not used. What the fuck? Oh, there's so many requirements here. A different pin may be used, but adding as parameter to the audio input analog object definition. A3, audio input analog ADC 1, A3. On Teensy 4, analog pins 24 and 25 are not supported. Noise due to noise due to high incidence, rapidly switching digital signals capacity higher, power supply rejection issue, simple DC bias, algorithm for automatic DC bias tracking, noise coupling from digital circuit inside the chip is always a problem. STONG, low impedance drive to the analog input, is critical to minimizing noise coupling. If an op-amp is used to connect a low-value resistor, 100 to 1,000 ohms, between the op-amp output and the ADC input pin. If a 1 nanofarad capacitor from the ADC pin to ground or a ground, the capacitor lowers the impedance for high-frequency noise, and most op-amps require a resistor to avoid oscillation when driving a capacitive load. Strong drive from an op-amp, 100 ohm resistor, 1 NF capacitor can greatly reduce the digital noise coupling. Okay, so that was all a bunch of waffle. Pass-through mono, peak meter mono, digital tone 7 segment, and spectrum analyzer, which is Octo WS2811, huh? With a spectrum analyzer. So that would be our spectrum analysis example. The question is, could I pull in some other kind of spectrum analyzer that I could use multiple channels on? Or if I do in fact need 2 more, I don't know how that works. I don't know if that works, having 2 more of these Jim Jams. There's only so many I2S lines. There's 2 I2S lines. One of them has multiple outputs, but the multiple inputs I'm not sure about. So we may need to do a little bit of research on that. But we can mess around with op-amp circuits first and build sort of the output engine coming off of these. And then we'll worry about building some kind of an input engine, and then we can look at solutions for bringing it into the microcontroller. There's got to be a way to do it. This is not a unique problem. So, and this is a very fast device. So we can look up like audio libraries for audio analysis and stuff like that. I mean, if I need to have one analysis engine running and be able to switch it between the 6 channels, I have muxes that I could do that with. I2S is weird. It works a little differently than that. Like there's the it's like the master clock, the left and right, and then a data line. So it's like master clock, left, right, and then data going to each thing. Because audio is a bit more involved. It's got a little bit of a different schema to it. It's sort of like a stream of data that goes into each device. Why are we on? Oh yeah, that's ground, right? Yeah, it's all a mess. It's a big mess. But I2S is, yeah, a lot more involved, and it's got a really nice bit rate. So using it for the outputs is great because this has sort of an inherent engine for it from all the programming from Paul Stoffergen. But the input engine that this has, I'm learning has some limitations to it. And it could be that maybe I only can audio analyze 2 channels, in which case we need to find like a mux that we can connect. Yeah, each data needs a wire because it uses up the full bandwidth. I was hoping we could have 6 independent inputs so we could analyze multiple different things at once, but it seems like maybe we'll have 2 channels of analysis, and then that can be flipped between all of the inputs using a mux. And we'll just see how that goes together. I have muxes. I have plenty of muxes. They're 5 volts, though, I think. If they function off of 5 volts and the audio input's on 1.2, well, it depends. I mean, if we use the ADC, maybe that'll let us R and L. We can take in 2 channels, and if we can just connect that R and L to whichever one is outputting here, and in turn, that would also take an external signal in and analyze it. Hmm. Because yeah, the functions of, I mean, this also does ADC, ADC. Oh, what's going on there? ADC1 uses ADC1 too. Okay. ADCS, PDM. Receive and filter a pulse density modulated bit stream. What the hell? Oh, it's a microphone. Oh, weird. TDM. 256-bit time division multiflex. Blah. What? Containing many audio channels. What the fuck? Weird. Huh. 256-bit time division multiplex frame containing many audio channels using the I2S2 port. So maybe that's the way you get many channels in. I guess they won't all be simultaneously connected. What is this song? Come on. I want weird, obscure techno, not whatever the hell that is. It's like game music. I don't know what that's from. SPDIF? That would be optical audio. Receive a 16-bit stereo audio from an I2S device using the second I2S port. So that's pretty much our stuff. 8-channel audio from 3 I2S devices using an I2S master module. master module? 3 I2S devices. Huh. Audio shield or another I2S using I2S master mode. And then this would be 2 audio shields. Yeah, so I don't know how much analysis. It sounded a bit like the DuckTales Moon theme. It did. It had that quality to it. This would be Counterpoint version 2 from Counterpoint. So it's not the DuckTales theme. It's called Counterpoint 2.0. The most replayed was the one we were listening to 2 songs ago. Huh. No. I don't know. See how we're skipping the B channel here because we don't have, I don't have it, well, I do have it hooked up, but I don't need 8 channels of output from this thing. We have 4 channels of potential output. I guess, well, no, that doesn't work. Yeah, I would need to have the mux in there. I can't do it with software. This is what the software looks like right now. We just have waveform begin here, and then we're letting the audio engine handle everything else. And then this is the GUI tool that has all the hookups where everything's plugged in. I don't know how you change those hookups. Like if I want waveform 3 to go to a different channel, it's currently connected here. So there may need to be some kind of like a switching kind of thing going on, or redefining of the waveform. So waveform 1 through 6 is just channel 1 through 6 output. And I'll need to be able to set it to nothing. In the waveform menu, there's also DC voltage level, noise, tone sweeps. So that kind of stuff needs to be somehow hooked up. Whew, there's a lot to figure out. Here's the analysis. Peak, RMS, fast Fouriers, tone, note frequency. Question is how close, how much can we get on this thing, right? I don't know if maybe I need to assign specific analysis to like an individual ADC and then use a mux to switch it from channel to channel. And then where would the mux live? That would have to live at a particular voltage level. Oh, there's so much to figure out hardware-wise. Luckily, this takes a lot of the complexity out of our hands. Although to be fair, maybe it might be easier to to do this on a lower level, and that way I would just be able to do all of these intrinsic functions instead of having to work it into Node-RED's specific way of organizing things. It's a scorcher today. This is a heat wave number 4. Heat wave number 4, and I think next summer we're probably not going to get individual heat waves. That's my prediction, is next summer we're not going to get individual heat waves. It's just going to be one big heat wave starting a little earlier than we expect and going a little later than we expect. And then things will be back down into the 70s and 80s for late fall. Isn't it grand? Isn't it really exciting? I hope you like heat and humidity around here. Because, yeah, heat wave number 4. I'm not totally certain what other summers were like, but I don't remember back-to-back heat waves with like 2 days in between. So that's what we got going on right now. That's what the music is. Just ancient tracker music. I'll try to find new music for Thursday. It's tough, man. I gotta find new music every single stream, huh? I need that like playlist of individual music that I like that I can just call upon. That's rights free. That aren't going to be all squirrely about my ability to play them on stream. Let's get the music out of here. Let's just get started. What's going on? Wait, let me just check on Twitch. We don't have a ton of viewers, but this stuff is well, this stuff is going to be kind of cool today. We get to figure out a bunch of stuff. Let's lower that down to nothing and hit pause. So people will be coming eventually. We'll have people coming around. I said earlier that, you know, I'm sort of on call right now just because stuff adjacent to me, pseudo family stuff is happening right now that I'm not totally involved with, but I am, you know, part of the support structure. So if stuff goes south, then I need to mobilize. So that is a potential thing that might happen today. It probably won't. There might be somebody coming to pick something up here, in which case the dog's going to go absolutely, you know, insane and things will get crazy. But who knows? They're not the person picking stuff up is not reliable. They're very flaky. So who knows? But anyway, aside from that, we have time to sit here and work with op amps. Op amps can be a little bit fiddly, but what they will do is they will allow us to build all of the proper voltage level signals that we need in order to build a Eurorack module testing module. What I'd like to achieve, and it might not be possible as per what I just read, what I'd like to achieve is the ability to have 6 channels that can be inputs or outputs and be able to do analysis of the waveforms coming in on those channels. And that might not be available. That might not be possible. It might just be that we can sort of have a couple channels that will be able to have full analysis, or maybe we can do 2 channels of analysis and choose which channel we apply that to. That would be something, that would be perfectly acceptable. So, oh good, YouTube does work. Op amps, yeah, we're gonna do a little bit of op ampy stuff. So what I have so far is a Teensy 4.0. And the Teensy 4.0 has this Node-RED inspired audio engine to it. And it gives you sort of advice on how to use the functions, on how to set up the hardware and stuff like that, all in the sidebar when you're working with it. Really cool if you're trying to do 2 channels of audio and do a bunch of stuff with it. But we're trying to build an analysis thing, so we're kind of pushing a lot of this stuff to its very limit. So we are stress testing every single element of this as we roll through. I have Octo output enabled on this thing. The thing about Octo output is that it uses I2S channel data channels to output to to 8 different, you know, audio outputs. So what you have is you have a bust clock and a bust left-right clock, and then 4 data channels. Problem with 4 data channels is that the Teensy 4.0, as a microcontroller, that's tons of pins. As a development platform, not all of those pins are brought out to breadboardable stuff. So in order to access that 8th channel, and I say 8th, but what I really mean is channel B. In order to access channel B, you have to solder to the pad under the microcontroller. It should have probably been called channel D. but it's for some reason called channel B. When you use 6 channels, it uses channel B. So if I were to use the 6-channel output node, I would need to run from under the board out. That makes this a little bit less of a plug-inable device. Typically, you want to just drop it on some pin headers, and then you've got all your I/O. But unfortunately, we don't. So this is channel B. So what I did is I used the 8 output, the octo output. And so we've got channel A, C, and D going into our I2S digital to analog converters. These things are pretty snappy. If you're building something like a guitar pedal or just a Eurorack module, these things output audio at plus minus 3 volts. Plus minus 3 volts is pretty cooked. That's 6 volt peak to peak. That's going to blow up a pair of headphones, right? I mean, I don't know if it would fully damage a pair of headphones, but it is line output, which is really, really cool. Now, considering that we are doing Eurorack stuff, we actually need these to function at plus minus 10 volts. 10 volts is sort of a sweet spot. Technically, really technically, if I really wanted to sort of revamp a lot of this stuff, I could do plus minus 12, and it would still be perfectly acceptable. Plus minus 12 volts you pretty rarely see in a Eurorack, because that's pinging the 2 supply rails. Some hardware can't really go that far. And in terms of analysis, I think I'm willing to say, oh, it's clipping. We're probably somewhere between 10 and 12 volts. And that would be like a failure state for a device that I'm testing. So we're going to keep it under wraps. We're going to keep it in plus minus 10 volts. That way I can use my 10 volt source in order to make the in order to scale the inputs directly to the analog channels of the microcontroller. Now the question is, like, interrupts and analog inputs. I don't know what exactly we're going to be doing with that. I hope I don't need to have a lot of clever switch gear in order to get all the channels running out at once. Ideally, in my mind, what I was seeing is that we would scale these to 10 volts, and then we would hook them up to a bunch of the channels that scale it down to 3 volts, and that would go into the Arduino. But according to what I'm reading over here, there's one input channel on this device. There's apparently one input channel, and it works from 0 to 1.2 volts. I don't know why. That seems kind of torturous. Why would we want to be squishing the voltage down so much? I guess it's to work with some mic modules that are used in more modern electronics. If we don't need an exact audio input, then maybe we can get 6-channel input. I'm not sure. I know analog. Ben Gizmo, can you please sit on your hands for a little while? Because what I was reading about is the audio input. And if we're going to do audio analysis, we're going to need the audio input. So on the inputs over here, there's ADC, out 0 audio channel. Receive audio using the built-in analog to digital converter. For that, pin A2 is used for audio input. The circuitry is recommended. Don't type shit if you just arrived. Don't correct me if you just arrived. How about that? That's a new rule. Jeez. Listen for a minute. So the control voltage is plus minus blah blah blah. Don't laugh. I'm actually serious about that. Okay, so analog read must not be used on Teensy 3.x. Audio input analog is regularly assessing the ADC hardware. There's some like pieces of advice for the Teensy or the Teensy 4 and the Teensy 3 in terms of using the audio input specifically at a pin. But audio input analog ADC A3, like, right, you can assign your one audio input. The analysis that I'd want to do on it is also included in here. So we actually do have those are filters and effects, peak detector, RMS, fast Fourier transfers. We have tone detectors, so we will be able to tune things, which is kind of important for doing analog VCOs, voltage controlled oscillators. The frequency, and then I don't know what print does. Print raw audio data to the Arduino serial monitor. Whoa, that's weird. I don't know what I'd be doing with that. I don't think I'd be doing that. Oh, good, there's blah, blah, blah in the explanations. Name, trigger, delay, length. So the question is, like, is there a library where we could use the Teensy 4.0 audio inputs, or the analog inputs, these guys up here. So the Teensy 4.0 analog inputs, putting our audio from our 0 to 3.3 volts into those channels and somehow still be able to achieve the analysis that we want to achieve. It seems like we're not going to be able to use the this tool to do it because, I mean, well, maybe we can. But it doesn't let me put down more than one ADC line. It doesn't let me put down any additional ADCs. Maybe I have to put them down and then assign them. Audio input analog stereo. 2, 3, and 3.6. So that's actually not my board. So ADC, this would be on a Teensy 3. What on Teensy 4 analog inputs, 24 and 25 are not supported. On Teensy 3, analog must not be used. Analog read can be used on Teensy 4.0 while audio input analog is running, as long as those pins are not used. Weird. A different pin may be used, but adding it as a parameter. What the hell? So we read this during the intro, but one of these is an audio input, or are they all? Analog read is input there, and then SD card, USB host. Not 5 volt tolerant. Cut to separate. R7 output 1, A1, R6, blah, blah, blah. 10, 11, 12, and 13 inputs for analog. CR1, PWM, SPDIF out and in. See, the alternative that we can do is we can use an actual ADC or DAC. No, ADC. These are the DACs. This is the ADC. So we could actually use an ADC to bring 2 channels in, and if we bring 2 channels in, then I can use muxes to connect to the 6 outputs here. I can actually show you the outputs that I was able to achieve with I2S using exactly what you guys just saw, using this. Check this out. Using this and skipping channel B because it's under the board and I don't want to run an extra. I did run an extra line for it just for funsies, but I don't want to use this. So we could do 6 outputs just by using waveforms 1 through 6, and I can reassign those waveforms using the whatever UI I end up coding. So I can reassign them and redo the outputs as I feel fit, or null the output and just have it as an analysis channel. So doing that, I'm able to get, let me turn on the scope. There it is. And then plug into power. Where's power? There's power. Power. All right, let's do a little bit of power here. And what these are doing is outputting individual waveforms that I have assigned to them. So there's our triangle wave. Our sine wave looking nice and clean. Nothing. There's another sine wave looking nice and clean. There's our sawtooth. And the sawtooth is a little dirty. There's a little bit of control systems-y things going on there at the peaks and valleys. So maybe a filter can tune that a little bit, but I'm okay with it being kind of a dirty sawtooth. That's okay, because these are audio outputs, not control voltages. Control voltages would be a hell of a lot slower. It's the same thing with the reverse saw. It's just doing that little kind of wibbly thing on the ends. And then square wave does something similar as well. And this is actually something that you tune out on the O-scope probes. I don't think it's my probes doing that, although I don't know if I've tuned this thing lately using, because there's a signal generator in the oscilloscope, and it's the tabs over here, at least on Rigol. It's the tabs over here. You hook up to these tabs, and then you tune your probes so that you don't get that wibbliness. We could actually check that. Let's check that right now. Let's check to see if it's my scope or if it's these brilliant little ADC lines. It is not my probe, even when it's not grounded. My probes are beautiful. They're beautiful and perfect in every way. Actually, they're not. They could use a little bit of a tune. Let's tune that just a little bit. Let's give that a little bit of a tune. I actually have the tuning thing out. Oh boy. Where did that thing go? There's something It's like a little, just a little like screwdriver looking thing. You guys see it? He asks as if people watching would be able to even begin to find something like that in this mess. In this mess. What a mess. So yeah, we're taking little baby steps. Remember, the name of the game is baby steps. We do one thing at a time, and we do it carefully, and we get it working, and then we move on to the next thing. And our goal is to stress test this microcontroller with all of the functions that we're going to then plug into a user interface, and that'll be the scope tester, right? So it's just this natural progression of steps. I needed a project like this where we can make these little achievements and it can still look cool on stream. So that's what we're doing. That's what we're doing. I hope you guys are ready for it. Where did that thing go? It was right here. I took the monitor out to a LAN party and we played Sons of the Forest 2. Which, oh, there it is. Hey, look at that. All I had to do was talk about something else, and then it shows up. We played Sons of the Forest 2, which I found to be very fun, except my friends don't do plot. They just don't. They don't do plot. And so, as such, I had no idea what was going on or what our goals were. But we do a lot of survival games, so we basically just... It was like the typical intro where you crash on a desert, on an island and have to survive. Like, all right, there's some freaky experiments going on. We crashed on this thing, and now we just have to stay alive. So we immediately built a forward operating, like, fucking mansion and got all of our survival mechanics dealt with before moving on to destroying the native population. As is typical in those games. I don't see what I'm adjusting. Am I adjusting the other side? Whoop, that was wrong. That was the wrong control. Let's move this all the way over. Yeah, I'm not seeing it. I don't see myself adjusting anything on channel 1. Oh, because this thing's in crooked. Holy shit. Really felt like it locked in there, too. I should be adjusting that curve. It's not doing anything. Try the other side. Yeah, I don't see anything doing, so we're just going to leave it as it is. We'll just leave it as it is. I think it's good enough for the analysis that we're doing. And I'll have to look into that later. I might need to swap out the probe itself. Might need to buy a new probe. I think that potentiometer might be damaged and unable to be adjusted. But it's not my probes causing these channels to look a little wibbly. They take a little bit to sort of get their voltage levels squared away, and that takes the form of what looks like... I mean, control systems do this. They do that when you transfer from voltage level to voltage level. You've got some kind of feedback function coming in there, and it goes... and eventually reaches it. That's where the analog stuff, like the analog wave generation, is really has kind of an advantage over the digital. But we are trapped in digital here. Why is my probe so hot? Sounds like a personal problem. Why is my probe so... Maybe just because I was handling it. God, it's like I got the air conditioning going full blast, and it's still nasty as shit here. It is disgusting. Disgusting! So we are at about 3 volts, right? And I guess that is right there. V max, 3.1 volts. So 3.2-ish, 3.3, we're kind of kissing. You can see it cutting off the waveform as it kisses that 3.3 volts. Now the amount of time displayed on screen is abysmally small. It is an absolutely tiny amount of time for that rise. The falls will look just about the same. So, and again, the fall, you can see that it maxes out at negative 3.3 volts. So I don't know what this ADC is doing. It's probably making its own negative voltages. What the hell? What? Hey, calm down there. That's the breadboard acting up. So what we need to do is we need to scale this to plus minus 10 volts. How do we do that? It's as easy as can be. All we need is our plus minus 12 volt signal, and that's what's not signal. The power supply for this device is plus minus 12 volts. That's typical of Eurorack, and it's done for ease of the circuits, ease of everything. We've got 6 volts is ground, positive 24 is plus 12, and then 0 volts is minus 12. You can think about it that way too, because it's all just potentials. Everything is just potentials in electronics. So what we're doing is we're deciding that we will have a power supply that assigns ground, plus 12, and then minus 12. So we have those voltages available to us. The TL07-2 or 4 or whatever, the TL07X series is a decent, just everyday op amp that operates as plus and minus voltages, and it can handle up to like 1 billion volts. I don't know what it goes up to, maybe 18, I forget. Either way, what we need to do is we need to put in some kind of a circuit that is going to bring this plus minus 3 volts up to plus minus 10. And then I am choosing a non-inverting amp just so that it makes it a little bit easier to output from here. I could do an inverting amplifier, and that would probably be perfectly fine. You know, you come in, you got one resistor here, and then you go up and over, there's another resistor, and then you have your op amp, and the minus is up top, the plus goes to ground, which is what inverts it, and then this comes out here, and that feedback is going to then be your output. You know what, maybe I do need to do it this way, because in here it's plus minus 3, and I can just invert that digitally. So a lot of the CV stuff that this would be doing well, CV is plus minus 10, so the gate would be a sudden negative gate trigger. And I think that's probably a cleaner way to do it. I don't know, the non-inverting op amp circuit, I don't know what advantage there would be to that. So we would have, instead of, we would have a ratio between these two. If this one is 100K, are we going up or down? What up, Lawn Dog? Watching and listening, but now I can focus a little bit more on what's going on. 100 kiloohms there, and then this would be in the range of 62.7, which is the typical value. I want this to be adjustable, just because I will tune it manually, and then I will have this, if everything works the way that I want it to, which it won't, I will have it be able to output a voltage from the DAC, measure it with the ADC, and tune itself so that we can display accurate values. I don't know what kind of accuracy we'll be able to achieve with that, but if I tune it with the potentiometer, then that gets sealed into the you do a lot of talking when you stream, and so everything ends up becoming mush. Your brains and your speech patterns become mush. It's all mush in the end. I haven't spoken to a human being in a little while, I guess. Okay, so oh, I don't have that screen available. Man, I need to be able to pop back to my previous scene. So yeah, we'll do an inverting op amp, and then this will be, that's 62.7, so it's 100K. And the ratio of 100K to 100K, nothing. Let's just real quick, I want to look up op amp circuits. Remember, there is no shame in going back and looking up stuff, right? I need to close some of these windows too. We're kind of a little we're in it deep. We're in it deep right now with all these windows. Oh yeah, that's right, the 23017. What was the voltage levels on this thing? I think this thing works at 3.3 volts, right? Don't get distracted. One thing at a time, baby steps. Close this. We can open that up later. The GE7000. Close that. I'm not doing screens right now. We're not doing screens right now. I'll pull this stuff up again if I need it. Pull this up again if I need it. I've got data sheets in a folder. Oh, jeez. They have you sign up. Noritake has you sign up in order to download stuff like this data sheet here. And then they email you about it. Hi, I'm your local representative of Noritake. If you have any questions, like, damn it. These days, research on ICs and other components and circuits is very valuable, almost mandatory for proper understanding. Oh yeah, there's a lot of hardware out there. Nobody can keep all the stuff in their head. Some do. They're scary people. I'm so pissed off that our screen is an I2C or some other easy to use thing, because it's not. Ours is like asynchronous serial. I actually turned on the synchronous serial, but the problem is Noritake made the screen that we have and then moved on and made more modern screens and stopped all support for our specific flavor of 7003. We just have the 140 by 32 7003. Noritake has a datasheet for a different resolution 7003. So I have to use that one in order to look up stuff about the screen and how to use it properly. Very annoying, but I got it cheap on eBay, so I guess I kind of walked into that. Anyway, I'm working on the screen separately. We're working on audio and op amps right now. So what I'd like to do is get in a tunable, actually I kind of want that. We'll keep that up. A tunable op amp that's going to get us to plus minus 10 volts. And we will make all 6 channels plus minus 10 volts. And then if we're outputting audio, we will then scale that audio down in amplitude so that it equals, plus minus 2 volts, which is, I think, typical of the Euroracks. I'm not totally sure about that. Although some have plus minus like 10 volt audio. Some of them really crank that audio out, so I'm not totally sure about that. Yeah, going and getting a catalog in order to look up the properties of stuff. Those days have been, those days are of yore. We're no longer doing that, luckily. We don't have to go look through 5,000 catalogs. So we're influenced by the Mutable Instruments module testing module, but we've gone totally off the reservation in this case. We have gone and started to make it into our own thing with inspiration from this thing. So looking at this is just sort of like a loose guide of the features. Like in the end, we want all the same features of this plus a little bit more, and that plus a little bit more is going to be our ability to reconfigure things and swap them around. So right now what we're doing is we're trying to get our proper CV outputs, and we need an op-amp circuit. So if I look up op-amp circuits, we have to do a little bit of math. Not that much math though. Top 10 fundamentals where we kind of live on this. This site is nice. It's got big diagrams of everything. So if we wanted a voltage follower unity gain, we could set something up like this, and as long as our op-amp can operate at the voltage levels that we're operating in, this will just output whatever comes in with a little bit of a delay. Not very exciting. What happens, the real magic happens when we're able to actually damp that feedback a little bit, and that gives us the ability to turn up the volume basically on our signal. So once we damp the feedback, we then have the mathematical equation of the reverse of whatever voltage is coming in is multiplied by R2 over R1. And in our case, R2 is going to be 100 kiloohms, and R1 is going to vary from 0 to 100 kiloohms. So if I have 100 over 5, then it's 5 into 100, right? And if we do that on the calculator, because I don't trust myself to do even the most simple of equations, because you'll embarrass yourself. Don't do math on stream. It's a very bad idea. So if we have 100 over 5, what that's going to do to our negative voltage is it's going to multiply it by 20. Maybe I want it the other way around. Maybe I want the other one to be the adjustable one, because then it's number over 100. We're dividing a number by 100. If we're dividing 100 by 100, that's fine. We don't want to multiply up. We want to multiply down. That's why I did the calculator thing, because I'm too dumb. So clear it all, and then let's do, it would be like 60 over 100. We're dividing 60 by 100, and we get 0.6 of our signal. So 0.6 of our input signal. So yeah, that was the wrong. This is why we check ourselves over. We wreck ourselves. So Z, 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 Z. And then this one gets the arrow through it, and this one's 100K. If I were doing non-inverting, this would be the circuit, and then that 62.7 would be the one that, because at about 62.7 is where we get the 3 to 10 volt thing. So, wait a minute, I was right before. I want to boost the signal. God damn it. 100K, and then this one's 100K, but it's variable. We're trying to boost the signal, so 3 times 20, well, that's ridiculous. I don't think that's exactly how it works. Negative, it's 3 times 20. That'd be 90. This is plus minus 3 volts, not 0.3. And I did 60 and I got 20. That seems wrong. Well, anyway, either way, we'll be able to adjust this and make this plus minus 10 volts. Let's see where that ends up. Let's set up an op amp to do this. So coming over here, I guess since we're doing a stress test, we kind of want all of our channels to be represented. So I am going to build 3 op amp circuits right here. The plus minus 12 volt rail is here. So I'm going to do this all right here. I don't know if maybe I should move the rail. Should I move the rail? And make this plus minus 12. And that way we've got our main outputs all over here. And I can bring this down to 3 volts. Because these are using 3 volts from here. If I make these 3 volt or 5 volt, then I can have the 5 volt circuitry. Well, the screen is 5 volts. I can put that all the way up here. Let me move this stuff out of the way. I think I am going to make the lower rail the plus minus 12 volt rail. We'll keep 12 volts further away from our microcontroller. I don't want to blow it up. Let's get the scope off the screen so you guys can see me actually doing this stuff. And then I can just move a lot of this stuff away so we can have a little bit of space. Because, yeah, I'll need to have the port expander running, and I'll need to have the knob doing its thing. We got a lot of stuff to implement in here. Oh, that's right. That thing doesn't like to move. It's like impossible to move. And this is my 10 volt source. So I'm going to take this thing off of being... I'll keep the grounds, but I'll take this off of the plus minus 12. And then this one is minus 12 that I need to get rid of. Keep the ground. That's actually wrong. Oh, no, yeah, the inner rail is always going to be ground. Inner rail, always ground. That's my hard rule about this thing. Although in this case, I kind of want the outer rail to be... And if I change that one, then I'm going to blow these up. Shit. I've made a huge mistake. All right, I'm going to keep this one plus minus then. Ay, ay, ay. Hey guys, cheap viewers. Stupid. Stupid, stupid, stupid. I can't just keep the inner ones always. I'll need to, I guess a dedicated 12 volt will go here. I don't like that. It should probably be down here where it's further away from everybody, but we'll keep this configured in the way that it was. So, unfortunately, I have to keep my plus minuses where they were. So, positive 12 volts is here. That goes to this rail. And then negative 12 volts will be down here. It's a little bit confusing, but we just have to deal with it. Oh, and the negative 12 is coming in. Oh, this isn't plugged in. My power supply's off, so I'm not going to accidentally blow anything up. All that's powering 3 volts is the Teensy, and that's what's powering the 3 audio outputs. I guess I should probably unplug that just to be nice. And then plus 12, or sorry, minus 12 here. And that's this one. So now that goes here. So I've basically undone everything that I just did. Is the orange one shorter? I think it is. Yeah, that'll do. That'll do. We just gotta live with that. Fucking goddamn it. It's like the Hydra. These fucking view bots. I got 40 people is apparently the sweet spot for multiple vectors of fucking view bots to come in. Gonad is gonna be thrilled with my progress. Okay, so let's get our TLO72s. I'm gonna need 3 of them. I think one of these is a TLO72. Let me just tweezer those guys out of there. Here they are. So once we get the 3 channels here running at plus minus 10 volts, we can then take a look at where we're going to input signals from. I would like to have all 6 channels available to some kind of an analysis engine. And that analysis engine will then be used on boot up in order to tune all of these voltage values. I made it. I'm finally popular. No, I actually, that was when I got the what is it? Oh, what was that game that everybody was sponsoring? Not League of Legends. Everybody had like a sponsor deal with this game. MCP 6002. Those are our input op amps. TLO72. Yeah, there it is. Raid Shady Legends. Yeah, I had a Raid Shadow Legends offer, and I was like, I made it. I finally made it. I'm popular. I turned them down because it's the opposite of the kind of thing that I think people need to. Plus, has anyone not heard of Raid Shadow Legends at this point? All right, so TLO72 operates plus minus 12 volts. It's also going to need a 10 volt source. So let's move that over there. Actually, yeah, move this over here. We'll give it just a little bit of space because our 10 volt source will go right here. And that's going to be used to scale the input and allow us to make a negative, well, what it does is it shifts our plus minus 10 volts into the negative, and then we have 0 to 20 volts that gets inverted and scaled so that it's on the positive number line. That way we don't get a negative voltage into our ADC, thus blowing up our microcontroller and having me have to go online and buy another one. It'd be very frustrating indeed. All right, I'm looking for the bin that has all of the chips in it. My through-hole bin. There it is. There it is. So we're implementing the full system. I'm going to put 3 amps on this. I don't have that many audio output plugs until we build the full thing, until I build the front panel. And I still haven't decided what I want to do with MIDI on the front panel, so I don't have that built yet, but I will in the near future. That's a TLO72. Need one more 072. That'll do. Now, I could put down a 4 and a 2, but I think that would maybe cramp things a little bit. So just 3 TLO72s is fine. 1 per audio engine. And we can take up a bunch of space. We'll just spread out here. Because I don't have anything else that's really going to use 12 volts. Everything else is 5 or 3. Give our circuit space to breathe. All that fresh air that we don't have here in the Northeast at this point. So I'll build up one of these, and then we just copy that circuit for the other 2. And they're going to use op amps because I want to be able to tune them. Now, what are those? I made circuits for my microphone that used op amps in some way, shape, or form similar to this. I should back up a little bit more. The camera doesn't zoom out any more than this, I don't think. Oh, it does. Well, it doesn't focus when I zoom out this far. It's only slightly claustrophobic, but this is what we got to deal with. And you guys get to see my disgusting breadboards. These breadboards, they sit for months at a time and accumulate stuff. Hey, you can see my little motor wire job here that I did to hook these up to 2 different, because these are going this way and these are going that way. I wish L and R were at the tip of this thing. It would make it a little bit easier to put down. But then again, putting a header over here kind of stabilizes it. I could have also used headphone plugs, but I think that's a little sloppy. It would have been nice if they had like a horizontal row like here so that I could plug into it, but whatever. I made do. I made duty with what I was given. Okay, so now these are inside of the device, and these are adjustments. So these get these these sort of instrumentation potentiometers. These are cool because they are 25 turns, I believe. And what it is a little worm gear that turns the resistive element inside. Now, if this were contained within an enclosure, it would heat up with the rest of the enclosure, and then that would skew the amount of resistance. So if we're talking about fairly sensitive amounts of resistance, it could potentially detune our device by getting warm. I don't know how much we're going to really have to worry about that, but let's get to building the circuit itself. Now, inside of this package, this die, we have assigned pins here for each output. So it's one, you have a marking on the chip itself, which is a notch or a space, and then you have pins 1, 2, 3, 4, 5, 6, 7, 8. They are anti-clockwise, or no, that's clockwise, isn't it? Wait a minute. Are they anti-clockwise or clock? This is clock 12, 1. No, anti-clockwise around the chip, and that's actually a holdover from vacuum tubes. You would have a space that indicates where pin 1 is, and you have 1, 2, 3, 4, and there would be no gap here, 5, 6, 7, 8. Yeah, it's anti-clock. Sorry, I didn't think about a clock. I'm a millennial. I have nothing to do with clocks that have hands. My parents actually bought a clock with hands to put in the kitchen because as a young kid, I was unable to read a clock. Just because everything was digital in the 80s. That's the claw X-Acto blade. Yeah, this is, well, I don't use X-Acto. I use scalpel blades. And so you have a variety of different scalpel blades depending on how the surgeon wants to split you into ribbons. And this is one of the ones that I was introduced to at just like a previous job where they bought a bunch of different scalpel blades. The cool thing about the scalpel versus the X-Acto blade, don't get X-Acto knives. They're a huge ripoff, and they're worse. They're objectively worse, and I'll tell you exactly why once I find that X-Acto blade handle that I have sitting in the drawer. So the X-Acto knife uses pressure in order to hold the knife in place, and a lot of different companies have copied X-Acto. I don't think this. Oh, this is a brand. Okay, well, a lot of companies have like copied them, but what you do is you put the knife in here, and then that pinches down when you close this collet. Problem with that, you can tighten this all day, but you're using this grip in order to manipulate the blade, and this grip is responsible for tensioning the blade in place. So as you're working with the X-Acto knife, as you're cutting things and maybe curving around and doing stuff like that, this will eventually loosen. It'll either loosen or it'll be a massive pain in the ass to change the blade. Both of those problems are solved by having the blade clip in. So that's what the scalpel blade does. It clips in, and it doesn't move around when you're trying to cut something. There are probably disadvantages to this, like maybe it doesn't hold it quite as well, or maybe there's a way you could get it to kind of like cam out. But for the most part, these have been super duper reliable, and they're cheap as hell. You can get thousands of blades for like $1. X-Acto knife kit. That came with an excellent handle and carrying case. But the thing is, like, scalpels solve all the scalpels are so much cheaper. It's such a better tool. Anyway, the point is, yeah, pins numbered 0 through 8, and if we look up the TL072, we can see what the pinout is. I might move my water. TL072 pinout. There we go. That's all we really need to know. Pins 8 and pins 4 are our plus and minus voltages. So we'll set those to plus and minus 12 volts. I'm not going to bother with a capacitor on that. You should probably have a capacitor on like a big audio device. A decoupling capacitor that'll just help it operate a little bit more cleanly, but I don't think we're going to worry about that right now. It should be totally fine. Those wooden cases are terrible. Nah, that's not a good kit. I don't suggest getting that at all. I would suggest getting scalpel blades. They're safer. They're safer because they're not going to let go of the blade, and that blade's not going to find your supple and easily ribboned flesh. I can't in good conscience tell people to try to buy that X-Acto kit. That kit sucks. It's terrible. I've used that all of my life, making stupid little things out of other things, and the amount of injuries I would have avoided at this point by just using a proper knife cannot be stressed enough. Okay, so let's get power and ground into all of these circuits. Now, do I have enough small jumps? No. I'm going to have to get one of these kits here. That one's like dead. This one's terrible shape. Let's put that over there. Let's see how many tiny little jumps I have. Tiny little jumps that'll get us to power and ground. Or no, sorry, positive and negative V. And actually, well, if I move these closer to each other, I hate this little gap in the rail. Very annoying. And it looks like I could go over one jump here. It looks too close now. Well, that's, if I move over one jump with that one, then I'm in trouble. Okay, let's go to here. Go to here, and then this one, I'll just center it on the power and ground. That'll do. So this goes to V minus, pin 4, and it looks like we need a slightly larger than yellow. So green is probably the name of the game. These are all color-coded, and they're all color-coded differently, the different kits. So you may get a kit that has like, blue is exactly the jump that I need. It's not, it's just the way it is. Some of the people in here will say you should go get a solid stranded wire and cut all of these yourself. And I guess there's something to be said for that, because then your layout would be pretty nice. Although having a homogeneous color for every single connection could lead to confusion. Homogeneous. Okay, get that there. Those are our negatives. Here are positives. Okay, some of these are not in good shape. There we go. The clips that are internal to the breadboard. There's this thing that Twitter's been pushing on me, and it's like this breadboard where you can assign all of the connections. So you basically plug your hardware into it, and then you tell it what connections you're making from what junction to junction. And it's got RGB LEDs on every single junction, so you can make all these, oh God, I bent it, and now it doesn't want to go in. You make all these like RGB connections and do all this weird proto work. It's very strange. I don't know if I don't know if it's a great tool. I don't really think it will be, because it probably has voltage limitations to those different jumps. And we do all kinds of stuff here. You know, I might be putting 35 volts through my through some of the junctions at some points, but I guess it probably is like limited to digital voltages, because it's probably using something like an FPGA or something like that in order to mux all the different inputs and outputs. But man, it looks really cool. It seems like it's probably pretty expensive though. Okay, so from there, what are we doing? Well, all of our pluses rather are going to be connected to ground. So I need to do pin 5 and pin 3 connected to ground. Now ground is a little bit of a shorter jump. Son of a bitch, you bastard. You've betrayed me for the very last time. We'll just do it like that. I don't like that, but that's what it is. That's what we get. That's what we get. So that one goes to ground like that. As soon as I can get these pins to align and properly plug in without destroying themselves. There we go. Unfortunately, the bean counters have found our breadboards, and we've got cheaper and cheaper materials going into these things. Cheaper and cheaper materials. We just got to deal with it. That one goes right here. My hand is fully blocking, isn't it? I'll move in just a second. There we go. You guys can get more of a straight-on view. This is less claustrophobic than the microscope. Actually, when I was working with this before, what I do is I take my office chair up to the desk so that my face was just right in this. I could see everything properly. Okay, so there's our plus input, our non-inverting input to ground on all fronts. So I now need a bunch of 100 kilo ohm resistors. I have a feeling some of the ones that are set up like this are going to be 100. Let's just double check some of these with the multimeter. The multimeter. Take that over to ohm. This guy goes over here. Make sure that that's visible. And then I can just use these to test these two. 100. Good. 46. All right, so you go away. We got 100. Now I have a whole thing of 100 kilo ohms, so we can obviously make a lot of our 100K feedback resistors. That's 1K. That's not even close. And I'm not going to go through testing all the other ones because we need this to be the feedback resistor, which means it needs to span 2 pins because it goes from output to minus, and output to minus is right next to each other. Pins 1 and 2, pins 7 and 6 are what we're going to be attaching those to. So I need a couple more of these things. One feedback resistor. And then the input resistor will be the potentiometer, and that's where we'll run all the channels to, and the outputs will go to whatever. I mean, I can run the outputs to the output plugs, like these. Put that like right there, and then we can use jumpers to get to all of them. And then let's see. Although the thing about that X-Acto knife case is that you can use the case to build stuff in, which I've done on occasion. So for $30, you get a knife that's going to cut you accidentally, and a case to go with it to build something. You try to cut the case with the knife, you're gonna get hurt. All right, so we need 5 more of these. One, two, three, four, 5. Wait, whoops, counted that wrong. Doop. Boop. All right, so these over here. So we just bend that down and give it a little cut. I'm going to make sure that those little leads don't end up on the floor, or else they end up in my socks. So that goes on pin 1 and 2. 1 and 2, 6 and 7. And 7. Why is it not? There we go. Jeez. Wasn't plugging in properly. As we proceed, continue on building this thing. Don't lose momentum. Keep interest. Keep it fun. Keep it exciting. This actually has to go here. There we go. So there's all of our feedback resistors. And then now I need a bunch of potentiometers, and I guess 100 kilo ohms is going to be all of them, because that's the value I need. And the question is if I can find 100 kilo ohms. Now previously I've done a little bit of work with audio and levels, so I have these things that I built. These are little frequency-specific op amps that have plug-in potentiometers. Maybe we could steal those, and I'll have enough of them for all 6 of these. What are the values on these things? This is for an EQ for my microphone. 103, so 10 with 3 zeros. So these are 10K, not 100K. I need 104. Damn. Are they all 103? They're all 10Ks? Probably. Yeah, they're all 10Ks. Okay, never mind. Never mind then. Fine. See if I care. So I need 6 100Ks. I don't know if I got them. There's 100K. All the way in this bin. I have 3. Well, let's get the 3 out. 2, 3. I mean, I could probably also use larger value ones, like maybe 200Ks, but what else do I have on the field? I'm looking for 104. There's 104, so that's 100K. 104, another 100K. There's your one. How many more? 1, 2, 3, 4, 5. I need 1 more. B100K. 103, son of a... All right, let's put that back in the bin. $204, 200K. 503, 550K. Oh, 504, 50K. 500K, rather. I was looking for something that I can watch and relax after a long working day. Feels like I've just found it. Hey, you know, Nourishing Soup. I try. I also try to freak out a little bit more than somebody normally would when doing this stuff, but that I end up being pretty tamped down overall. I generally don't freak out that much, although my chat has told me to calm down on a few occasions, which I find funny because I don't want to calm down. I want to keep this stuff fun and exciting and weird. It's a whole thing. But yeah, we're just working on circuits here, nice and quiet. Trying not to disturb anybody. So 104, 10K. Let's get those into the input to the two different circuits. Now, one of them has to hop over a couple lines, and the other one I can do almost directly. No, that's to hop over one. So I guess we're going to pull it out into the field area and then put the potentiometer on it. You're doing great. I don't need your pity. Oh, I'm getting a side cramp. Shit. Lately I've been getting these diabetic side cramps where like some muscle on the side of my body just goes, well, I guess I'll die, and then it just cramps completely, and I have to sit here like this, like doing this because of the lactic acid buildup. You need to like calm the muscle down and like stretch it. Get it to get rid of lactic acid. So I'm sitting here like, yeah, I'm a totally normal person. There's nothing weird about me. Stupid. It's because I'm hunching over this stuff. So yeah, we can just install these like this and just keep them on the right side of each one, and then the left side of each one will be the input. I think it's a little close, but I think that'll be okay. I'll have to buy a bunch of potentiometers for the final thing. Actually, let's move it over one. Let's give it a little space to breathe. A little space to breathe, so I don't want the components that are in this area knocking into each other, because that causes all kinds of strife when you're trying to build stuff on a perforated prototyping. No, on a solderless breadboard. When you're building stuff on the solderless breadboard, you don't really want stuff to be colliding with one another because that'll cause things to be a little bit more unreliable. And when you have unreliable circuit connections, that leads to massive amounts of frustration. This is a big mess. I probably should have cleaned this up before streaming. I need one more 100 kilo ohm potentiometer. 100 kilo ohm. I would highly appreciate if you can share your train of thoughts when you're troubleshooting reverse engineering something. I had a grooming tool. It stopped working due to water damage. I'm a software engineer, but reverse engineering electronics is a whole new world. Yeah, I mean, so, man, there's a whole thing behind it because I've been reverse engineering circuits for 10 years of my life, and I do have a whole spiel about it, but it's not as prominent in the project that we're working on right now because we're not reverse engineering. We're building a tool that will allow me to better reverse engineer and fix my buddy's synthesizer. But generally, when I'm reverse engineering something, I am working backwards from... Well, okay, forest for the trees is kind of the first thing, is power and ground are going to dictate the operation of most of the circuit. If you're looking at a PCB, if you're at the point where you're looking at a PCB and you're like, why did this thing fail? The first thing to check is to look at all the integrated circuits and figure out what they are. I mean, okay, step 0 is to look, is anything burnt or charred? Because the failure mode for electronics is heat. Generally what happens is some kind of a cascade of resistance causes a whole bunch of heat to build, and then the magic smoke goes away. So you look at your capacitors. Are the capacitors blown? You look at your chips. Are any of the chips showing something like a little pockmark that looks like that goes down into the substrate? So if you have something that looks like this, that chip is dead. That a dead chip right there. What the heck happened to this one? I hooked this up wrong and it blew up. Then you can look at the markings and stuff and see who makes this thing, what it is. You might be able to look up and find a circuit or find a common failure mode of those things. If it's water damage, I'm not quite sure about that one. If it's water damage, you're going to look at all of the, basically trace the power line and look to see if any of the components along the way have exploded, because some resistor could have gotten some kind of muck across the leads, and then it becomes either more or less of a resistor, probably mostly less of a resistor, and that allows things to short out and get over voltage conditions and little blown up components. So it's at that point, if you're then still having trouble and you haven't found a specific failure after, of course, cleaning the board and getting all of that contaminant off of it, you're down to like powering the board and testing where voltages are coming in and seeing what they're doing. If not, I mean, before that, even you test whether or not there's a short between power and ground, and looking for any schmutz that might have caused that. Then you're down to looking at the chips that make the thing work. So the chips, if they're identifiable, you can get the part numbers off of the top of the chip and then look them up and see what the data sheets look like, and then see whether or not the chip is doing what it's supposed to be doing. It gets fairly involved, though, at that point, and that's where we are with Dave's synthesizer, is that I've had to go through and fully reverse engineer the circuit so that I knew where I was and what I was testing. And that led me to the revelation that I don't have the proper tools to test modular synthesizer modules. This has been something that kind of came up in our mutable instruments module building, but it's something that's very prevalent now, is that I don't have all of the stuff in order to consistently test Dave's module and figure out whether or not it's working. And then after that, I would like to have something that allows me to tune Dave's module properly, and in turn test my own. That's a 104. We're stealing this. I've never used this. I've never used this little breadboard helper device, so I'm going to desolder this and use that. None has exploded. Some solder is a bit damaged. You can reflow that and see if it comes back. There's a small LED that glows green while I hook it to power, so it's kind of charging but never works. Battery seems to be dead. Well, you can take that battery. I would take the battery out, first of all. Other than that, you know, if it is a new device, it's going to be a lot less repairable than if it's an older device, because older devices have chips that do things, and newer devices have ASICs that you have like a blob of epoxy sitting over a raw piece of silicon that's been deposited on the board, because the volume manufacturing is so much cheaper that way. So there's a big difference between new and old. Big difference between new and old. Now, keep in mind, that was under duress and trying to be as succinct as possible in giving the explanation for how to both repair and reverse engineer something. There's more to it, and I think maybe hopefully I've given you enough that experience will eventually be had. But it's like forest for the trees. You want to start at the most likely easy stuff to fix and drill down eventually into knowing what exactly is there. But like your visual inspection of the board is going to be the most important thing, and then tracing power to stuff, and then figuring out whether chips are blowed up or not. Because like the chips, the more complicated circuit elements are usually what fails, but the resistors and capacitors usually will give you a nice indicator that they've failed. But beyond that, time is money, economic maxim, no free lunch. Don't waste too much of your time if it's a cheap device. Sometimes the tools in order to troubleshoot the device are going to cost more than just replacing it, at which point, you know, while factoring in gained experience, you're still wasting your time on something. That's sort of the revelation that I can't have with Dave's synthesizer, because Dave's synthesizer has insulted me, and it's now a personal vendetta against this fucking thing that I get it repaired. But like in terms of repairing Dave's synthesizer, going through chip by chip and just replacing everything would have saved me months at this point. But also, I wanted to have a schematic for a Moog at the end of it all, so an M303 rather. I wanted a schematic of an M303 that wasn't as complicated as the one that that's on the repair manual, And I guess I'm getting that into CAD so that one day I can sit down and design a circuit board for an M303 of my own for much less than $600. Yeah, that's sort of the exact thing that we've been working on here. Perfectly reasonable hill to die on, but I would have tossed it out the window by now. I should have taken it to the healing hammer. Oh, there's still an excess of solder on this. What the heck? Yeah, it should have seen the healing hammer a long time ago. But it's about sending a message at this point. Give me all this excess solder on your pin. What is this thing doing? I need to add flux. It's not getting into my solder braid. Weird. Get in there. All right, there we go. How to use your multimeter when you don't have any schematics? So the particular rules to follow for the initial troubleshooting. Don't use the beeper, use ohms. Always use ohms. Look for areas of the circuit that there may or may not be solder breaks. Measure through components. If you have a resistor down where you seem to not be getting ohms from point to point, take it out from those points. So like for instance, if I've got, and I've run into this before where it's actually been a problem, where I've tried to go from, all right, let's just do this as a quick example. I'm gonna do a quick example because this is stuff that I really know about and I do kind of want to show off. Oh no, the leads of this aren't long enough. I may have to solder it to a header. Oh, that might barely do it. Okay, so coming out here, come on out here to the vise. Yeah. So if I have scorch marks near a resistor, well, these components are kind of small, but whatever. We'll do it on the tiny ones, and hopefully it'll show you the mentality. Because basically what you have is you have traces that are connecting from point to point on a circuit board. The traces connect from point to point, and they have pads, and those pads can separate from the trace. So what I would do with the multimeter, you know, I have no idea what the circuit is, what it does. I would start with power and trace that around. And then look at the individual ways that things have failed. But what you can do is you can go from, for instance, a pad to a pin, and I've got very low ohms, right? Or I can go, let's say, from, what is R6 connected to? I think it's probably ground. So go R6 to resistor to ground. That is 98 kilo ohms. So that seems to be this 104 resistor right here. It's a little blurry, it's hard to see. We don't have the stand light on. But if I measure across the leads of the resistor, I get 98 kilo ohms. Or if I go from a big ground to this lead of the LED, I also get, okay, that's totally different, 195. What's going on there? Try over here. 435. I guess that resistor, I would think that this resistor would be associated with the LED, and I wouldn't get 195 kilo ohms. That seems a little weird to me. Maybe this is a pull-up, or no, it's a 1K pull down for this analog output. 339, 241. That tells me that it's probably going to the chip. So from ground to this resistor here, we have 98 kilo ohms. So then this would be the ground connection for that resistor. 195. Okay, so this is, you're starting to see what the process is here. That does not go to ground. Does it go to here? Does it go to A0? No. How about over here at D0? Is it a power indicator? Is its first stop positive? 99.4K. There it is. So that's positive voltage to the resistor. So is this a pull-up for A0? No. Pull-up for D0? Why is it all the way over here? No, that's not right. D0, where else would that go? It wouldn't go to an LED lead. 99.5. Anyway, so the point is, testing it like this, you get to know what's connected where to your powers and grounds and what the circuit structures look like. A lot of it is experience that I'm drawing on in order to test where things are. But like if you test point to point, you see here I get point, 0.8, 0.7. So I can tell that this is connected to power. Or no, sorry, it's connected to ground. Wait a minute. Connected to power? Yeah, this goes from positive. So then this lead goes over through this resistor, and I can test the component through other leads. So I can go from here all the way to the other side of the resistor, and I get 1K. If this trace coming off of this side of the resistor is broken, then I need to verify. So 1K to D0, no. 1K to positive, is it a power indicator? No. 1K to ground. Okay, this is the power indicator. So the power indicator goes, as we've seen, from positive on this lead to ground on this lead, which is kind of a weird way to hook it up. I don't know why it's hooked up like that. And then these two just connect to one another through there. So if this trace here were broken, and I know that this is a power indicator, and I trace the actual physical trace over to G, and I test from here to here, and I get nothing, I would get OL, right? If it says OL, then I know that something is either broken in the resistor or at that trace. And if that trace is broken, I can scratch up the little bit of the trace outside of the pad and do a solder bridge over to it. I've done that before on the subwoofer project. So the point is, probe around, figure out what's going on, write it down if you need to. With the subwoofer project, I was at my wit's end. I had no idea why this thing would not work. It seemed to have a vendetta against me. And I was looking around, and just for the hell of it, I started poking the multimeter on stuff. And eventually I found exactly what I just described to you, which is a trace that had broken, and it didn't look like it was broken. So yeah, it's one of those things, like, there's a bit of an element of luck to it, but if you probe around, you can get to know it. If you find you're wasting your time and you really, really want to get to know that circuit, you can then reverse engineering it using all of that point-to-point stuff, and by looking at where the traces are, without desoldering stuff, there's going to be hidden surprises underneath any ICs. But I don't know what type of electronics you're looking at. If you're looking at something with lots and lots of components, you can do that. But if you're looking at something with a couple of ASICs, it might not be that repairable. But have fun, poke around, see what you can learn. There's always something surprising. Okay, so now we have all of our tunable boosting circuits where we can put all 6 of our channels. How am I going to get all 6 of the channels over to that stuff without making an absolute bird's nest out of this whole thing? Oh, wait, we're not even using this. We're not even using this. This is for the inputs. Negative 10 volts is for the inputs from these outputs. But these outputs will be going to all the plugs. And so now I need to send all of my audio channels to those where we can then tune them. So I guess we'll be using longer leads for those, not totally long ones. God, this is gonna be a total mess. Take that there, put that into one of the channels. Not the best organization I've ever done. Oh wait, but I also need to hook up the whatchamacallit? I need to hook up all of the pots to stuff. So hold on, let's do that first. I mean, something that I can talk about for years. I can talk about reverse engineering until I'm blue in the face. I mean, I could move that one over a little bit and give us a little bit more breathing room, because we're not very close to all of this stuff. Oh, okay, hold on one sec. I gotta go deal with something. Where's my BRB? BRB. I'm back. That was a delivery, not what I expected. Oh, okay. This should be in view somewhere. Get rid of BRB. All right, back to building the circuit. We can spread this out a little bit more. I think I need to do that in order to get it to fit. Move this over here a bit more, maybe. It doesn't matter that much, but I guess it'd be nice to have it sort of moved over. No, you know what? No, I'm not going to do that. We're going to keep it spread out. Maybe I can run all of the outputs to like a thing over. Well, actually, all the outputs should go here so that we can plug them in like this. Yeah, I'll do output all the way in the corner here. And then the outputs from all the op amps should come here. And then I'll run the inputs here where we can just skip them over to where they need to go. I think that's the best way to do it. We'll just do, you know, like hop, skips, and jumps over to the different areas. And that'll just keep things a little neater. So the outputs of these are on these pins. Where's my tweezers? Outputs are coming from here and here on each one. So I need to route those down to basically this area here, and then I'll be able to jump them over to our output plugs. All right, so outputs will go over and down, over, down, over, down. We got some room for that. Now I just need to choose the form of the destructor. Too short. Oh, this is... So one of the problems with these kits is that you don't get much mid-length wires. That sort of middle distance that you're going to be operating in on such a big circuit like this is just not there. It's not represented. So like if I do that one to... Yeah, that's my only choice is this wire. I don't have one that's slightly smaller than it. The yellow wire is too short. Is there another mid-length? Not really. Yeah, that's all I get. So just try to keep that neat. The name of the game is neat. You bunch of neats. Wait a minute. No, that's not the right use of the word. All right, this is way too claustrophobic. Hold on. We got to work with it like this. That's the only way. The only way. So like that, and then I'll focus. You guys can see what's going on. Why is that focal distance so... It's so narrow. It's like this is going to be in focus, but this won't. And it's not that much of a distance change. The distance change. Bend. Go from the output there down to here. This is so what this is doing is basically saving my bacon from troubleshooting woes. The neater and the more organized I make this, easier it's going to be on my future self to troubleshoot. Do I need a resistor on the output? I don't think I do. Maybe it's just polite to do. There, so those are that's the one channel of outputs. Let's do that. Not quite. Well, I guess it doesn't matter. I can use it. Yeah, I can do that. Do that. 1, 2, 3. All right, so that's all our 6 channels of output. We can then tune. Now I need to route the inputs. So input coming from... Oh wait, we still need to connect the potentiometers. That's where we left off. So I need a short jump to get to the pot. from the negative input. So from negative input to there, and I guess that's just the yellow. These are going to be in very short supply, these yellow jumpers. If I have anything just slightly longer, which would be green, which is the other one that's not available. Do it in a blue? Too long. Too long. Okay, so yellow or green, I guess. Maybe we can use... I'm not using as many greens, so maybe I can use green on that one. I have multiples of these kits. You buy them in big packs, so... it's almost not worth recycling them. You can just buy a new pack, which really makes you kind of feel bad. You're like, yeah, well, I'll throw all the old jumper leads in the ocean. I guess the yellow ones I'll have to use on the top piece. So from here to there. Yeah, just throw them at dolphins. Like your car batteries. You're gonna have to move. Yeah, this one's a little bit more restrictive, isn't it? Yeah, that gets to that lead. Well, I can always bend up the third lead on that one. Just like that. These get yellows. Going to the negative input to the input lead. It's a little bit more narrow than that. I don't know if the slightly shorter jumper will do it. You can sometimes get these to stretch just a little bit further, but unless I move those closer, I guess I'll have to move them closer. Closer by one. This. And then these guys. It was annoying when your design has to change due to limitations of components, like what you have in stock and what you don't, especially when in regards to jumper wires. So I do envy the people who have a big spool of solid conductor wire that they use in order to cut their own custom lengths of jumpers. Yumpers. All right, so that's those inputs. The leads on this one are very annoying. Let's go right there. Oh no, that goes here. I guess I'll pull this one in a little bit. So output is there, input is here. Oh no, that one's larger. What the heck? Oh, come on. Don't fight it. There we go. All right, so now inputs I want over here. So that's probably going to go up and over everybody because I can't go down and over this space. See, what I did up here is I really tried to not have jumpers going on top of other stuff. It's not a requirement, but it's just something that makes it nicer to work with the circuit. I don't think I'm going to be able to accomplish that here. These will be red, go all the way to the end here. And going through the rest of the circuit is going to make it kind of way too busy. Well, here we go. The red's even too long. It's just something slightly... I could probably cut these in order to make them fit exactly. The other part about this is that I don't know how long these are going to be here. So it's possible that I'm going to need this part of the circuit to hang around for a long time, and the more three-dimensional it is, the less it's going to stick. That's too short. See if I can route them up and down like that. The other part is if I have a sensing part of the circuit, I guess I'm going to have to use the wire jumper. Hey, Noisemo, how's it going? We're doing the output stage of the audio, the digital to analog audio components. So these are the inputs here that I'm wiring with the red wire, and those will come from all of our audio channels right next door. I'm trying to make them have a wire run that isn't totally crazy so that this circuit has a little bit more longevity to it. Unfortunately, I don't know how much of that I can actually accomplish. I've been able to get 6 digital outputs with the DAX. That's kind of a little crazy. I don't know. Hopefully that does okay. There. That. And maybe another blue. It probably should be red, actually, coming from that one. There to here. Red's a little long, but I think blue's a little short for that jump. I did not get the VFD working yet. There's a little bit of, I mean, I've got this like Windows 95 looking program that should get it functioning on the serial port. I've just had a little bit of figuring out to do, and in the meantime, today we're working on the audio input because it's just easier. It's easier to get running. That should be green. That should be a green wire. And then I guess this one should probably be blue. Bring these down here like this. And then this one up. Blue and then a green for our last input. Get out of the way. All right, so these are our adjustable input channels, and that allows us to change the output voltage of everything. Oh, it looks like this one doesn't quite reach as green. Okay, well, that one will be a blue. 2 blues. That screen is going to look amazing. I wanted these to have, well, okay, fine. Yeah, that'll have to go there. And this one here. Up and around. Probably should have installed them in the opposite order, because having this one jump over 5 different lines is going to make it pop out. But for now, we'll just keep it like it is. For now, it can stay, and it'll be a little bit annoying. So our inputs are over here, and our outputs are over here. Now I can wire these up to all of the inputs, so I guess with depreciating wire lengths, these are all I have. This is the only mid-length wire, and that one doesn't drop down as much as I'd like it to. I want it to go down and over. I may be back busy day. Hey, yeah, do your stuff. Do what you gotta do. Don't let me hold you back. That screen is going to look amazing, but it's going to be very involved to get together and functioning. Dang, why isn't that thing going in? I could do all the same wires and have them go like fan outwards. I haven't used a lot of the green jumpers, so those will just be what we use here. And if I give them enough of a run vertically and horizontally, or rather enough of a vertical run, then they don't like crash into each other and pull each other out. Some people just use these things on their whole breadboard, and it becomes this huge bird's nest of connections. And you know, that's okay. I've seen that, and it's okay. There's nothing wrong with that, except that I find it to be an absolute nightmare to troubleshoot. So I appreciate running everything flat along the board, but then when you interconnect multiple things, it starts to get very busy. Even in digital electronics, it gets very busy, and you have to kind of problem solve in order to flatten everything out. And the neater you make it, the easier it's going to be on you in the end. Guess I didn't have to use the green ones for this one, but it's fine. It's fine. It's fine. Now we got plenty of space to drop it and look at these signals if we need to with the scope. Okay, so now we've made a ×6 audio amplification circuit using 3 TL07 2s. We used 6 TL07 op amps, and now we can tune these so that they are tuned to ± 10 volt output. We know they're all outputting unique signals, so all I need to do is turn on my scope here, which is pretty good at measuring stuff. And it's likely that the math is going to pretty much dictate how this happens. I currently have the D to A's outputting at full amplitude. You put a number 1 in there, and they output at full power. So I give ± 12 volts to my output. Now here's the part where I am at an advantage to your average circuit builder, and it's not something that I like to brag about because I actually like to appeal to the everyman here and say, hey, look, this stuff is not that hard. You guys can do this. Well, not everybody has a webcam speed thermal imager. So in this case, first power on to a circuit that I built on breadboard, on solderless breadboard. We turn it on and we see whether or not stuff heats up. Now, if you guys are doing this just on your own, if you've got like a 12 volt hookup to a breadboard that's like a wall wart, I would advocate plugging it in really quickly and seeing if anything happens. Maybe looking at your circuit elements to see if they're heating up. I poke test the chips. You probably shouldn't do that. You can get a pretty bad burn doing that if something is hooked up wrong. Double checking your circuit is probably your best bet. You go back through, you take a break, drink a whole pot of coffee, come back, and then you go, what's hooked up the wire in my circuit? But you come back and you take a look at all the individual elements of the circuit, the really boring stuff that you don't want to look at again, and you make sure that things aren't cross-connected. In my case, what I'm able to do is turn this on and see if anything heats up. Alternatively, I could go to the power supply and I could limit the amount of current that the power supply is going to output. I could do half of the amount of current that I expect things to draw, or do 10 milliamps and then 20 and then 30 and 40, stuff like that. You come in and you give it little tiny drip feeds of current and see if the power supply shorts out. A benchtop power supply is probably the most useful thing in this case, because then it has a short shunt that gives you a little piece of information about whether or not things are working properly. But in my case, I'm a streamer, so I full send 12 volts to the thing, boop, and we see if anything heats up and explodes. Nothing heats up and explodes, so I guess I'm getting good at this stuff. It is drawing 0.002 amps, so 2 milliamps, and nothing is exploding, which is on a level unfortunate. We expected stuff to explode. So I've got my probe here for the outputs, and I can take a look to see whether or not we don't get anything. Oh, because I'm not giving it a signal input, because the microcontroller is not currently hooked up to 12 volts. So if I hook the microcontroller up, we get nothing. Oh, I'm looking at the wrong signal there. Oh no, that's not ground. This is ground. This is ground. This is our output. I get nothing. Good day to you, sir. What about over here? Okay, there's our signals. I guess we zoomed in a lot. Let me zoom out. What is that extra trace on there? What is that? Is that a math trace? Why is that even there? Oh, that's a measurement trace. I see. We get nothing. Good day to you, sir. Check to see. Nobody's getting warm. Nobody's even getting warm, which is typically how they would be in operation. Now, it could be an adjustment thing. Let's check all of our channels. Oh, wait, what's going on there? That's going to the wrong thing. That might have blowed stuff up. I don't want to blow up my ADCs. These are $11 for 3. Really? Ah, okay, so there's a signal. That one's hooked up right. So is that one. Nothing, nothing. So second question. Yep. Was that a result? So these might be cooked. They might be much higher voltage levels. So we'll take this out to where we can see plus minus 10. Push on this thing a little bit. That's connected in, and it goes into the... Oh, the feedback's on the wrong line. No, wait a minute. Oh, I see. I'm plugging the input into the wrong thing. Okay, so this one goes, and I get a yellow jumper. Shouldn't do this while powered on. Let's power it off. So this is where you vet out little mistakes in your circuit building. Yeah, I desperately do not want to... I don't want the magic smoke to come out of these, and especially not my microcontroller. I want to be real careful about that, because these are not cheap. They're not terribly expensive. They're not prohibitively expensive, but... Yeah, that's what drives the pluses and the minuses, is all that magic smoke. Very important to preserve. See, that doesn't do it. And then the yellow one is too restrictive. But the green one is not, is larger than yellow. It's got to be a yellow. Got to be yellow. The alternative is to move down a little bit, but I don't have space on this part of the board. So from here to there. Actually, that was the perfect distance. That was the perfect distance. And then this doesn't plug in because the lead is... Ugh. Okay, hold on. Move this up. No, I can't move it up because there's a thing there. That goes to ground. Yeah, there's no space for the potentiometer here. I can solder it to a couple leads, I guess. Where's one that sits really nice and flat? Take this one, maybe? No, that needs... These potentiometers are kind of like wide, so they need to sit above the wires that go in. And this one doesn't have the leads to do that. There, that's in there. Okay, now they're in there. Okay, so checking on this one. That's going to the right spot. That's going to the right spot. Let's just see what we got. Oh, there's a wave. Okay. What about the upper one? There's something there. We'll get it back. That one has a thing. That one has the thing. Okay. And then this one is blank. So let's double check it. Input there to there. Into this part. Goes to output. This goes to ground. And that goes to negative voltage. This one goes to positive up here. So maybe it's there and we just can't see it. These, we have the unenviable task of adjusting all of these. And I thought I bought a specific tool for adjusting. I thought I bought a specific tool. Can you guys tell I'm from Philadelphia? Am I doing a little bit of a Philly accent, a little Delco sound in there? Jeez, I thought I bought. I actually did buy a tool to adjust potentiometers, but I think I lost it. I think it sucked and I threw it out. I'm not sure. Or did we? No, didn't we find a tool that adjusts potentiometers? We found this one. That's not for pots, though. I guess maybe it could be. It's a Wago screwdriver with a little belt loop. Huh. Not that great. Not for instrumentation amplifiers. Thought I had a tool for this. it basically would cup the end of the pot so that your screwdriver wouldn't slip off of it when you're doing adjustments. So you don't have to constantly look at what you're doing. That's this one. Let's see if we get anything out of it if I adjust this either direction. Huh. This channel is being fed by the first one here. And I don't see anything on it. Why don't I see anything on it? That's going all the way out to here. So just taking it up the line until I see something. What's going on here? Hey, wonky robot. Well, microcontroller, this is a Teensy 4. Hey, Keeper of Maps, how you doing? Why are we not outputting on this channel? Reset the micro. Well, same deal. They've all got power. They got signal. Did I blow this thing up by hooking it up to stuff? I think it's blown out. Yeah, I try for that. That's very intentional. We saw earlier that I was outputting a signal from these, and I am hooked up to ground on the probe, and the probe is hooked up, and we can see other channels do output stuff. Is this, did I kill this? I might have killed it. Yeah, neither of these are doing anything. I mean, I can set up, I've got one last one that I can hook up. Unless I didn't do anything to the code. It would be the module itself that blew up somehow. I don't know how though, because it's not like I didn't hook it up to anything controversial. And like that's our waveform. So waveform 1 and 2, which I defined as a sine and sawtooth. How can that be? Well, is something particularly hot or not on the module? The module gets warm. It runs warm, and it's kind of hot. Why is that so hot? Why is that running so hot? It's powering I2S. Could it be that there's just not enough power to power everybody on the 3 volts? Do I need to bring in a 3-volt regulator? That might be the case. Yeah, that would be the PSU. How much current can this thing? Well, okay, I don't think it's a matter of current output. Oh, yes it is. Look at that. Keeper's got it. That's exactly what it was. Okay, so we need to bring in an external voltage regulator. External VREG. There's not enough 3 volts. There's not enough 3 volts in the planet for me to run you. So we're going to take an LM1117. Now I have those in my micro miscellaneous bin. Yeah. Listen, I've already had words about backseating. Opening the stream and immediately making a suggestion. Don't do that. All right, so I need to find the LM1117 boards that I have. I should probably have, yeah, here's one. I found it. These are the 1117 3.3 volts. It's an okay regulator, the 1117. It's all right. I don't love or hate it, to be honest. Makes about 1 amp of current. And so we can plug that in, and we'll use this as our 3-volt supply for these boards. So I'm going to actually get rid of this. Did I just There's no way I just shocked myself. Everything's disconnected. No, I think I just poked myself with a lead and it felt kind of like a shock. So I'm going to get rid of this 3-volt connection as a whole. Now, this is still connected with ground, so they share grounds. So that voltage potential at ground is the same everywhere, right? Everybody knows that as a reference. So now I need to get positive, probably 5 volts would be safer. Well, the 1117 can run from 12. It can run from 12. I would like to have it right here, but this might be a little bit close. Also, I don't have a great connection to ground over here. Maybe move this like that, and then get ground. Ooh, let's see. A little greeny. I'm not going to be able to figure out where to plug these in once I unplug them. It's in-out ground, I believe, so I can do this. And then the one... Shit, which one was which? Goes like this. I have a 50-50 chance of getting that right. What's my pinout on this thing? In-out ground. Okay, so... out ground like that. Oh, this barely fits. Jeez. In-out ground, and then out I need to jump over to where 3 volts comes in. Let's get a green on that one. I don't have scraps that I can use, so let's just find one over here. Where are my yumpers? Let's try these. This is a mess. Slightly longer. So that's out here. V in there. Is that correct? Yeah, that's correct. Okay, and then we need positive 12 or positive 3 or positive 5. I'm not sure which one I want to use. We probably should just use 12 as if this is the final thing, in which case I don't have a positive 12 line anywhere but right here. So if we go here, I'll go down, out, and around to here. This stuff gets more and more complicated, and it becomes more and more of a bird's nest. So positive 12 here to the input right there. And this is what a lot of the synthesizer modules do. They just take 12 volts from the positive 12 line and they make their own 3.3 or 5. So in this case, we're making 1 amp of 3.3 and we're sending it out over here. When we do the other circuit, the one that's going to tamp down an external signal and send it to the Arduino, we will then use this same 3.3 volts. So I'm going to need to run it to other places, but I guess it'll exit somewhere over here and just go up and around or whatever. Ooh, I gotta drink liquids. Hold on one sec. All right, so let's try that again. 12 volts on. All 3 of these lit up. This thing's lit up. Nobody's blowing up. Nobody's blowing up. Hook up the Arduino. Computer didn't blow up. Nope, everybody's fine. Output. Nothing. Okay. Output is nothing. Why would that be? Because maybe the Arduino isn't powered up properly? I didn't blow up the Arduino. It's simply not outputting 3 volts. But that should still be under ground reference. So I should, by all means, still be getting... This thing is an unperturbed LM1117. Oh, do we have an LED on the other? On the one that I made 5 volts? I don't even know. We have the LED, I just don't know if I saw it turn on or not. Maybe we should double check that voltage. Uh-oh. Yeah, that looks like 3 volts. Yeah, 3 volts, okay. That's a nice little 3 volts. it shouldn't all need to power up at the same time. If I start sending it I2S, it'll just get I2S. They're all connected to the same ground. I mean, it's shared up here. Ground there, ground there, ground there. So they all have the same voltage references, so those input signals should be going into the I2S just fine. Oh, did that not plug in all the way? Was that it? There's data. There's data. There's data. Output. 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 What the fuck? 3 volts. 3 volts. Signal. Signal. Oh, no signal on that line. That's this one's signal. This one's signal. And that's this one's signal. So these modules are getting power. Why are they not outputting it? Why would they not be outputting it? They're getting everything they need. They're getting a different 3 volts, but they should be fine with it. Oh, unless these are 5 volts. Oh, maybe these are 5 volts. Hold on. Bleep. Oh, you know what the other thing is? No, you know what? I think they are 3 volts. I think they do function at 3 volts. No, I think I mixed up these 2 lines. The M bus and the other one. That's what it is. I'm going to turn everything off. So I'm going to flip these 2 wires. Now it should function. I did the old switcheroo. There we are. So signal, 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 signal. There we go. Okay. So now we can actually tune the outputs. Let me plug these back in. This is a full feature test, so we're doing everything big. $50-50 connections? No, what was going on is the when I unplugged these 2 in order to put this voltage regulator in, I flipped the 2. I plugged them. I had a 50-50 chance. Yeah, right. That's what I was talking about. You're correct. You're correct. My brain is just on different frequencies. Okay, so now we can actually tune these and get them all to do plus minus 10 volts with their input signal. So whichever one I'm plugged into, I can just go to the potentiometer and bring that out until my Vmax is 5. Sorry, I said plus minus 10. Shouldn't it be plus minus 5? Whoa. Okay. No, it's plus minus 10. It's just that some of the mutable instrument stuff says plus minus... Is it plus minus 5 or 10? Yeah, the DACs have multiplied. I'm doing a full 6-channel test. For the plus minus 10 volt signal source, that would be for a plus minus 5 volt in. Because plus minus 10, no, plus minus 10 volts, because you've got only 5 volt offset, but if you shift the whole thing by 10, then your negative 10 is 0, or your positive 10 becomes 0, and your negative 10 becomes negative 20. So no, that's not, okay, so for plus minus, we want plus minus 10 volts. Okay, sorry, I just routinely confuse myself with this kind of stuff. So we want that Vmax to equal 10 volts. And our VPP will be 20. Am I allowed to show my VPP on Twitch? Is that like a VTuber's junk? Bring it down a little bit. With this, I can very carefully do little tiny bits of twists and bring it down to 9.9 or 10 or whatever. And the thing is, like, this is going to drift. While these are instrumentation potentiometers, that adjustment is going to drift. And so I want to plan for that. And in doing so, what I can do is when we figure out how to drop in on these channels and test them with our own test equipment. So we will be able to test what this thing thinks positive and negative 10 volts is by making the DAC give it positive and negative 10 volts. That'll also tune it. External signals might be off by a little bit. But then again, like, the whole point of the module tester is that it's got the ins and outs. When I really need to get voltages, I'll get it from here. But the module tester should be able to do, you know, 90% of these tasks with a little bit of drift. It's not super duper tuned. I wonder if a DAC, no, an ADC, I wonder if an ADC would be better tuned. If I could find like a 6-channel ADC that uses I2S. I don't know how that works. I guess you can only do 2 channels on I2S. Each line can only do 2 channels, unless you have multiple outputs. So I'd have to have multiple inputs, which this doesn't have on the other channel. It only has 2. So the other scheme for dropping in on these channels and looking at them is to use this ADC, but have some kind of a way to mux it into all the different inputs. And then we would have 2 channels of sensing that could be on display at once. So 2 audio input channels that would be configurable. I want to keep this thing configurable so that future me can deal with the layout. All right, drop it in on the next one, and we'll get that tuned to the tune of not millivolts. What's going on here? So this one was this. So our square wave is over here. And then what do we have next to the square wave? We have invert sawtooth. This is showing nothing. Good day to you, sir. Oh, because this popped out. It's a little shorty one that keeps popping out. I wish I could find something for this, but I have to like press it in order to get it to make contact. No, this isn't doable. All right, so let's put a pin header on this one. I need to put a pin header on this one so it's a little bit less obnoxious. We simply get a pin header from the bin. This one will do. And then I'm also going to grab the female pin header because I want to plug this into something for soldering it. I want to plug it into something in order to solder it, and that way it won't melt and the leads won't get weirdly spaced. So we grab those 2 things and hold on to it. Clamp it up. Actually, you know what? I could... no, the female... Well, they don't stick in as well. You know what? We could do this without soldering. We can do this completely without soldering. All I need to do is get a 3-pin female header of the type that I use. Oh, here it is. Grab this too. I just need to grab 3 pins of this, and I can just plug the short leads into this, and that'll give them a little bit more depth. Actually, it's just about the same, but I guess the female lead fits a little better in the thing. So just do that. Let me pop that off. Where'd my cutters go? All right. This one will tend to pop out because just the nature of these things. But this will hold it up a little bit too, so it won't collide with my leads. Oh, this is also not plugged in. I could also explain it. There we go. Now I get triangle wave. Yeah, I mean, I've run into that where the contacts get very tired after some time. But no, in this case, it's because the legs, I desoldered that from a different like thing, like a breadboard sensor that I didn't like. And hold on, 9.6, 7, 8, 9, 10. It's not because the clips are tired, although I have run into that before, but it's mostly because I desoldered it from being a through-hole PCB device. So it was on a through-hole PCB, and I removed it, and so the leads had already been clipped very short. So that made the necessity of putting a pin header underneath it. So our triangle wave is at nearly, maybe just a little tiny bit over 10 volts, and then our square wave is just maybe nearly, but just a little tiny bit over 10 volts. Mostly below is what I'm looking for. So now on to the next one. Let me get this ground wire out of my way. Put it over here. Okay, so this one is a sine wave. We can get that tuned up. The whole purpose of this is to get all of the scale of the device together. I want to get all of the stuff out and make sure that, you know, everything is as it would be in the final design. The final design is probably going to be a bunch of the perforated prototyping boards. I have the section that'll have all of this stuff on it, and a section that'll have all the input stuff on it. 9.789, 10, too far. Bring it down just a little, bring it a little bit down from that. .7. It's a little tight. That's a little tight. Let's bring it in a little bit more. There we go. 10, 9, 10. Touching the circuit is going to affect its parameters as well. Yeah, that's less hot. Holy shit, that thing's on fire. How much current do these things draw? Why is that so hot? What's going on here? I'm going to need to get the big 3-volt regulator. Damn, these things take up a lot of current, huh? This thing is, the whole circuit is drawing 100 milliamps. Holy crap. Why are you guys so crazy? What's going on here? I don't think I'm drawing that. The 3 volts is only powering these guys. That's crazy. 100 milliamps to run these 3 things. So, all right, so that one's at a pretty good voltage level. Bonk. That one's approaching, but it's middling. It's mid. I have to put a finger on these to adjust them. When they're in the final circuit, I should be able to just twist the twist the adjustment, and it won't pop off of the board like these do. You can use a fixed amplifier ratio and adjust the max output voltage in software. The whole purpose of having the adjustment in here is to get it to the max range, which might drift over time, and allow me to have the maximum amount of adjust from these 3. And then if I have a feedback circuit where I can drop in on the channels and adjust and measure them, then I can scale them in software properly in order to have the right voltages. But if these don't, if values drift over time and I don't have full authority with these things, then there's no purpose of it. Yeah, 1/10 of an amp on these digital devices that are running audio. I don't understand why that's cooked in that way. Why is that drawing so much? And it's not like I have any other circuitry running at 3 volts. Unless I accidentally plugged something into... No, there's nowhere else that it can go. It just daisy chains up this line. So these things are hungry hippos. 33 milliamps for each one. That's a 10. This one is at 9.9. The other thing that I could do is also allow the DAC to drop in on the 10-volt reference source. So if the DAC can drop in on the 10-volt reference source, we know this is very accurately 10 volts. My plus minus 12 volts should also be extremely accurate, but I mean, whatever. I can have it jump in on -10 and say, hey, software, here's -10. Hey, software, here's ground. And then it can make scalings for each one internally. Yeah, we're doing a little bit of crypto mining with these things. It's not like they're getting hot, so they're definitely using all of that. Strange. $10 volts. Let me come over here, test this one. What is my glucose level doing? I think I forgot to bolus for lunch. Oh no, it's actually corrected itself. That's nice. Spam. Someone at the door. That's a doorbell. There's somebody at the door. I wonder if a person is supposed to pick up something picked it up. Maybe Willow didn't make that much fuss. The thing that I went and got was a box from Chewy. 7, 8, which means there might be a squeaky toy in there for Willow. Willow loves squeaky toys, but they do not last long. You gotta debate whether or not $15 is enough entertainment for the dog. she will immediately eviscerate it, get the squeaky toy out, munch on the squeaky toy, and very reluctantly give it to me in exchange for a milk bone. So she's gotten very good at that. And then what she did with poor Lamb Chops, she ripped off Lamb Chops' face like a fucking serial killer. Like you could wear Lamb Chops' face. Frightening. That definitely ended that song. Song that doesn't end my ass. This thing is over. All right, why do we not get signal here? We get you coming in, and you're not coming in. Oh, I missed it. That one is there. So there's our triangle is there. Our triangle is here. Yes, sir, yes, sir. Which is actually down here. Oh, that's that. And then this one should be triangle. Triangle, correct. Triangle, gone. Okay, so it dies with this. Why aren't you bringing it over to the other pin? What the heck? Is it like a dead row? What's going on? Oh, or is it being grounded? I didn't hit the right pin. Okay, so correct that. Circuit issues. Oh, that could also be why our 3 volts is being tanked. No, that's going to the right pin. It's not going to a ground. It goes over here. And then it just kind of dies there. So we should be getting triangle here. Okay, we are getting triangle there. Blank there. So if I pull this in like this, and I test it on the output, nothing. Into the nothing. Nothing. I should be getting it right here, but I'm not. Is there something wrong with the TL074? Or is it a matter of feedback and I'm just not seeing it? Let's see here. Well, no, because if I look at it the other way, if I unplug this and plug it in 1 row down, and I look at it right here, it's not totally gone. It's actually at the right voltage levels. Is it just a cursed? No, you know what? I think it is here. I think it is here. I just need to adjust it out. Ah, Jesus. I got that did I actually get the tool? I don't know. I think I got the tool specifically for adjusting these because it's got like a little collar around the flathead, and that collar would hold it in place on top of these things instead of it camming out of the flathead screw. Very, very annoying. Let's go back this way. So like I can almost see the wave in there. There it is. Yes. Yes, there you are. Wow, that jumps up really quick. Jeez. Why does it jump so hard at the end? Wait, it's only going to... What value is this thing? $104. So why would it jump so much at the very end? Is everybody hooked up properly? Let's check here. Well, the other one's adjustment range was okay, so the other op amp in the circuit. That's output there on the right pins. This thing says 104 is its value. TL072, that pin definitely goes to ground. That one goes to positive 12 volts. The input comes in through the pot and then goes over to the output with the feedback of 100K. If it's not 100K, maybe that's doing something. Check 100K. Check that feedback. My multimeter is tangled, and I cannot check the feedback. Hold on. Get my multimeter out of here. Turn off the circuit so I don't blow it up. Hello? What is it doing? Oh, there we go. Output off wouldn't work because I had it displaying the limit. Yeah, test this one. See what it is. What is? 1K. Aha. Okay, that's the problem. So we need to get a 100K. That was just a 1K. Wrong value. Let's check this one. $50K. Let's just get another one off of the line. He had 2 sets of testicles, so divine. Washington, Washington. 6'20" made of radiation. That's the wrong line. I skipped the line. Ah, old YouTube. Let's see. All right, so that goes in right here. Now we should get all of our adjustability back. I can't believe that guy went on to have a whole ass cartoon show on Adult Swim. All right, so now we have our range back. So if I turn this back on, 1, turn it on. There we are at above 10 volts. We'll just bring it down. The value of these is probably all about 60 ohms. And while I could just put fixed resistors in, I do want to make sure that my upper limit is properly adjusted for. What's going on here? I should be seeing a change. Damn it. I keep slipping off of the little thing. Oh, I hate these so much. I'm gonna have to get one of those adjusting wrenches. That's not moving at all. Let me go the other direction. Whoa. Oh, did you know that we actually had a triangle wave? 97, 98, 99, and 10. So we'll bring that down just a little bit from 10. There we go. All right. Yeah, I know. Wrong way is always the issue with those. You always go the wrong direction. Yeah, what I need is a like a little thing that envelops that brass adjuster and has just a line in the middle. And I tried to make it with my 3D printer with the FDM one, and it didn't really do a great job. So I would have to, maybe I can use the resin printer in order to make a little, like something like with a hex on the outside, and then it would have the cup and then have the line through it. Or I could drill this one out and put a pin in the middle. Just put like a wire from one end to the other. Nah. Okay, so those are all at 10 volts peak to peak. Sorry, 20 volts peak to peak, but plus minus 10 volts, which makes them CV capable. So now I can use the DAC in order to output either audio signals or CVs on 6 channels. Since this thing has 6 plugs on the front, that means that any plug will do at any time. The second question is whether or not I can get any kind of analysis off of an audio input channel, off of an analog input that is scaled to those plus minus voltages. So basically what happens is I take an MCP 6002 and I run 10 volts into one part of it, and I run the input signal into the other, and then I have plus minus 3 volts coming out of the, or sorry, 0 to 3.3 volts coming out of the other end. So let's pop this out of the way because we're going to be working. I mean, honestly, I probably should have built this stuff here, and then I'd have here for the, that's fine. It's fine, it's fine. It'll just be a little bit constricted. So, MCP 6004, the question that I have is whether or not I can run multiple audio channels without muxing. What I found earlier today, I read and was very discouraging, sorry, over here is that, oh wow, I have a lot of PMs. What's going on? Who's messaging me? Oh, LAN party stuff. Wait, oh, plus this stuff. What's all this? Oh my god, Bing Gizmo's been busy. 6 in, 8 out, or even 8 in, 8 out via a single TDM connection if you wanted to with an example like this. This is a hackaday.io. This is from Bing Gizmo, who knows a lot about this stuff. So yeah, this is that TDM thing that I ran into while looking this up. But many channel audio IO with TDM. Audio IO, maybe you're doing personal audio sound effects using the 8-tab direct effect where ordinary stereo or even 5-channel surround isn't enough. Maybe you're making an ultimate Eurorack synthesizer module. Kind of doing a little bit of that. Hey, what's up, Flatulent Gonad? How you doing? Oh, there was something that tickled me pink earlier that was something that you would absolutely have appreciated, and I don't know what it was now. I totally forget. It was 1,000 years ago. I don't remember. Oh well. Lost forever. Here's the board. Cirrus Logic CS20... CS2448. This is probably not the direction that I'm going to go in with this. If anything, what I would do is... oh my god, what the hell is this thing? Super duper audio codec. Stock, not available. How much does this thing cost? An obsolete Cirrus Audio codec chip. Not that expensive. $40 still. 44 bucks. Little man, put that shit in my hand. There's a little tiny chainsaw. Look at that little guy. NXP, Audio EXP. So it's, yeah, so it's not cheap, but it's also not prohibitively expensive. Look, I know that this exists already. The thing is, like, I want 6 individual outputs that could also be configured as inputs. So I could use an audio codec on I2S and do an analysis on 2 channels and then mux that over to the other ones. So yeah. All right. Let's see. Yeah, here's Paul Stoffrigan in the comments. Is it possible to do the following? Connect the boards from the computer using software, sending 8 more audio streams. Huh? Weird. All right, let's close that. I don't think I'll be going this route because it's buying more stuff, and I don't want to buy more stuff. I think I have everything I need in order to produce a pretty nice audio device. The question that I have is whether or not I can get the analysis that I want out of a channel that's not necessarily catered towards audio. If I can just do analog inputs and I can get all that I need out of that, because then I can have all 6 of them connected at the same time and I can do all kinds of shenanigans with it that way. Otherwise, I can limit myself to 2 channels, have the I2S input, and use the teensy tools in order to get whatever analysis from those channels that I need. So I can have audio level signals. So let me look up a piece of that to see whether or not I can actually do what I want to. The Max 309 is the chip that I have in just huge quantities because of a brain monitoring project that I did a long time ago. So let's take a look at the Max 309. That's actually probably the 308 that I want. But 309, well, actually, no, depending on... Oh, I just want the data sheet. These are getting kind of old, but like 8 channels, although it's either 4 and 4 or 1 and 8. So I don't know which one I would necessarily want to use. What are the input? So Max 308, 309 is a precision monolithic CMOS analog muxes. mux. So that's CMOS. So that means 0 to 5 volts, which is not going to work out for us. These muxes operate with a single +5 to +30 supply. Actually, they might work. Or bipolar ±5 to ±20. We are ±24 volts, though. So we could power them off of +12 to ground. Hey, what's up, Pyro? How's it going? But I want them to be able to operate within our limits. A single +5 to +30. We're ±12. Oh yeah, so ±12 will work with ±20. CMOS inputs, though. Are they supposed to be... Well, the control inputs. So yeah, ±15 volts is their limit. So this will absolutely work in this system. Analog signal range, 0 to 12 volts. Oh, it doesn't do ±? B+, B-, those are the limiting voltages. Operational supplies other than overvoltage protection. Do you go negative? Do you go negative? Do you do that? We could just test it. We could just test and see. Just add a resistor. Bro, just one more resistor, bro. See, like, if... Oh, man, it's 4, not 6. So that would be really useful for 4 channels, but I need 2 more channels than that, so I'll probably have to use the 8s. Transistor count. 100. They did this within 122 transistors. How about that? How about them apples? Meter, impedance analyzer equivalent, channel select. So I wonder if this will work in our ± environment. Well, I've got a couple on board, so we can plug it in right now and see. Let's just plug it in right now and see whether or not it actually functions. Unfortunately, I don't have any room around my ±12 volt stuff. This one is at +12. I could maybe put this one at -12 and we could just hook it up here for right now. This is connected to ground. Let's unhook that. Make sure there's nothing hooked up. And the microcontroller doesn't talk to any of that. So we'll just see whether or not we can use a fixed channel and put one of these signals into it. These ±10 volt ones. We used these on the keyboard project, and they were being used at, I believe, they were being used at 3.3 volts, which is the lower end of their voltage input on DC. Actually, wait, they're all DC. Eeny, meeny, miny. This one. There it is. The worst thing about Maxim chips is finding real ones that aren't ripoffs. You can get better, like, Maxim. This chip is obsolete. This chip is from the early 2000s. There are better ones now, but yeah, I've never run into the fake Maxim chip thing. I imagine that's a thing. Maxim chips are expensive, but they're all so specialized. They're so, like, they're just so nice to use when you're dumb and you can't think of any other solution. When you're dumb, it's nice to have Maxim chips. Which one is this one? You 308 or 309? Can barely see that. Okay, so 309, and then this one's a 308. Yeah, 308 and 309. So let's just hook the 309 up, and we'll just have it go to a fixed output, and we'll see whether or not it can handle the voltages that we're giving it. What's up, Madam? Man, everybody's coming out this afternoon. You guys all, like, infect the internet at 3 p.m., don't you? Oh, my buddy got to drive a K car. Son of a bitch. Look at this. Look at him go. Oh, that's so awesome. I want one of these. I would drive this around. Because I don't do a ton of driving anymore. One of these guys, that little thing. Look at that little thing. Oh, I love them. I love them so much. They would have completely taken over the market here in America if it weren't for stupid truck laws. It's a very easy manual and road legal. More attention than a Ferrari, he says. Although right-hand drive would be very annoying for me. Oh, that would be fun as hell. Okay, so Max 309. We're hooking up a Max 309. Max 309, our pinout is as follows. Where'd the 309 go? There's 308. Scroll, scroll, scroll. Scroll, scroll, scroll. I thought the 309 was on the same data sheet. Maybe it's like all the way... No, it wasn't all the way down. I thought we had a universal data sheet. What the hell happened? Maybe I didn't scroll up enough? No. 308. Am I taking crazy pills? I'm taking crazy pills. I somehow we're on a... What if I click back? It's like, yeah, 308/309. What the... I'm taking... Oh, it's not until all the way down here that they show you the difference between the two. I see. I see now. I delivered mail for over 30 years on the right side. Makes no difference once you get used to it. I do have a buddy with one of the less flashy Skylines. Or no, GTR? I don't know, whatever. But it is right-hand drive, and he's totally used to it now. So, yeah, I don't know. I guess you could probably make sense of it after driving for a little bit. It would just feel natural. I like my left-hand drive, though. I like being in the middle of the road, not the very edge. Okay, so let's get this thing hooked up. So we need ground, V plus, and V minus. So we need the whole suite of voltages here. So we have V plus over here. So if we hook this one up to V minus, which is this one out here. So this one goes to V minus. Oh, I should turn everything off for this. Off. No more digital. There you go. Probably should, you know, just to be nice, just so we don't blow everything up if I happen to cross connections. V minus is pin 3, so I'm actually going to flip this thing over so we can get to the minus and the plus a little bit more easily, since we've inverted everything on the center of it. This is not the best put together perforated prototyping board. Not the best put together circuit I've ever done. The things are a little bit janky. Better than you do, though. Jerks. That's right. You're catching strays today, chat. I'm always the one catching strays. You're going to catch the strays now. It's your turn. All right, so yellow gets us to ground. Ground is on pin 15. Where did that go? Right here. Boy, the mixed voltages in this device are going to be absolutely mad to keep track of. I'm not going to create a circuit board. I'm not designing a circuit board. So 16, 15, that one goes to ground. Actually, I can make that a little bit smaller. Too small. Well, we've been doing that with the yellows, so we'll keep doing that. So pin 16 goes to here, 15 goes to here. It needs to be a little bit more narrow. Have I been muted this entire stream? I've just been muted, haven't I? Yeah, I've been muted for 2-3 hours now. All right, so there's ground on that side. The other grounds that we're going to have to hook up are the muxes. 1A, 1B, those are those, and then V minus, V plus. A0 and A1 I'm going to put to ground, and that's these two here. A0 and 1 do the switching for this one, which is the 30... Wait, is it 308 or 309? This one's the 308. I want to be hooking up to the 309 just because it's going to be easier with the address pins. Although, no, the placement of the 309 needs to be a little bit easier for me to hook up. Sorry, we're doing a lot of stuff at once here. A lot of thinking going on. That. And so now I have on the right side, I have A1 and ground. That's these two. So I'm going to hook that up to the ground pin, which is not, okay, so this is flipped. So I got to be careful here. That was not a connection to ground. I need to actually go a little bit further over to get to ground. What I'll do is I'll actually run a jumper locally for that. So I'm going to go to ground to pin A1. Gotta be careful about that. That can cause troubles. Plus 12 is right here. A little flat one single jumper right next to it. Dang it. There we go. Ground A1 and then V+. Name suggestion for it. Module testing, module. It's going to be something like that. I'll guarantee. Module cubed. Okay, so there's V plus to the positive. Now I need a V minus to pin 3. That's on the other side of the board. 1, 2, 3, 4, 2, 3. Go. And no, that has to be all the way out there, actually. I need a green for that. So green there, pin 3. God, the parallax when you're working with breadboard is very extreme. Because things that sit on headers are very tall. And if you're looking at them from just the wrong angle, you can get all of your pins off by 1. Ask me how I know. Actually, don't ask me how I know. Enable. What happens with enable? Enable does not have a line over it. Enable does not have a line over it. A0 and 1, we're both putting it at 0, so we're just going to output to 1 channel. So I'll use the common and go to the 1 channel, and we'll run our voltage, our signal through it and see what happens to it. 0, 0, 0, and enable at 1. So it needs to be at a CMOS 1. Logic 0 is less than 0.8. Logic 1 is greater than or equal to 2.4 volts. So we're going to take 3v3, I guess, and run it into that. Yeah, the tables are nice. They're nice and easy to understand. We need to run 3v3 into... See, I was just using grounds, but I guess we need to have that 2.4 volt. It says greater than 2.4 volts, but I don't know how much greater than 2.4 volts. So I am just going to run microcontroller 3 volts into the enable pin. Yeah, let's get this thing. Had the whole breadboard sitting on it. Because I don't want to run it from all the way over here. I'll run it from here. It's slightly closer. There we go. Jeez. I don't know what it is about streaming, but words just like leave my brain. What pin? We're looking at pin 3. I remember that from earlier. So pin 3 here is my 3v3 out. That doesn't reach. Much longer. Get one of these. Enable is pin 2. This one here. Over to pin 3. That's going to enable our chip so that we can actually see the output. Otherwise, the connection isn't made. These are meant to emulate a switch, so they like fully disconnect and then connect to where they're going to. We use them in signal acquisition for light sensors that were on the frontal lobe of the brain, and they would give you a light level for near-infrared, a near-infrared LED that was pointed into the brain. And the thing about the specific frequencies of near-infrared light is that it went through bones and stuff and bounced off of blood. So you'd be able to see how much blood a particular frontal lobe was using. And that allows you to measure, well, sort of relatively measure the amount of activity in that part of the brain. You can see if somebody was thinking real hard about something. and when that activity drops off. Okay, so from there, we are going to take one of our signals here. So we'll take one of our signals here. Any one, doesn't matter. We'll put it through the scope. And I'm going to run that to the A terminal, which is unfortunately on the other side, so I need a longer jumper. Use this nice big old jumper from A, and we'll measure it at B, like that. And we'll see what we get on the other side of the scope. Moment of truth. Power on. Oh boy, that's not good. Are they heating up? No. Not using a ton of 12 volts. But our input should not be at a high level. Why is it at 12 volts? Here. 16, 15, 14. 16, 15, 14. 14 is at 12 volts. This one is at 12. These aren't. Do I have the wrong maxim? Okay, let's turn this off. What's the difference between 308 and 309? Maybe I have a 308 plugged in. A1, A2, ground, V+. We might, actually, that is the 308, isn't it? It is the 308. I got the pin out wrong. A1, A2, and I need to jump another one and move my positive. So this moves down. Oh, good, it can't, because there's already something there. Well, or I just take, hold on, I've got the other chip in here is the... Nice of it to not blow up. That's very kind. Typically things would be like, ah, and then blow up. So nice of it not to do that. Oh, I'm getting a side cramp. Don't you cramp on me. Yeah, we're going to be breadboarding for a little bit. I can't wait to actually build the hardware, but so that one goes to ground. That one is definitely ground, yes. Double check here to see ground is the outer pin. Yes, ground is the inner one on this one. So that goes A1, A2, or no, it's A0. Sorry, we got to go all the way back down to the 309. We're using the 309 just because. A1 ground V+. So A1 and ground are connected because we're using the first channel. So A1 ground and then V+. And that goes to this one, which is the positive rail. And then our input signal should be going into, our sense signal going here to channel 1. Channel 1 right there. Okay. So then we go over here and we have A0 on pin 1. So pin 1, A0 connected to ground. Then we have the enable pin, which we're just piping in a 3-volt signal from over at the microcontroller. And then the third pin is V-, which goes to the outer rail here, which double check, that goes to V-, correct. And then this is our input on N01A. Electronic components used to be mounted on little, like, what looked like light bulb sockets that you would screw into something. And so people would build circuits on boards that were meant for cutting bread because they were cheap. There's a cheap wooden board that you would cut bread on top of. And since wood insulates, a lot of prototyping circuits were built on insulative bread boards. And so this breadboard got its name from that. Although this thing uses plastic and little clips, and you would not want any food items on this ever. That's where they come from. It was very nice of it not to go puff. Yes, it was actually quite polite of the 309 to not immediately explode in the face of having a weird differential between two of its pins. Luckily, this thing operates at a voltage differential far above what we have even available to us on this board. Hold on, my esophagus! My diaphragm has to invert itself real quick. Okay, I'm back. All right, so let's see. Let's get this thing chooching. Let's get it pumping out stuff. That's not your word, bother. You can't use that word. That's a Canadian word. I'll get some of this stuff in here. Yeah. Okay, 12 volts. Bam. Of course, nothing happens because we're not giving it a signal yet, but everybody does power on and nobody is exploding. See a little bit of a heat. It's just reflecting. So give it a signal. Come on, buddy. I see nothing. There are our waves here. Here's our wave here. That is going through this. Huh? No? Well, we don't see a positive 12-volt signal at the very least. What are wrong? Oh, I think our minus and pluses are backwards? Minus is on the left side of the board. No, that's correct. On pin 3, here, minus 12. Oops, wait, this is my signal input. Oh, yeah, right, okay, so minus 12, correct. Plus 12, correct. Ground. And that's 0, 0. So what that says, what's up, That Your Fan? How you doing? Hey, That Your Fan, it's been a minute, hasn't it? Or have you been here the whole time? You're like, I've been watching for weeks and nothing has changed. So we're going in NO1A and, oh, we need to be COM A. COM A is down here. So common A, we're going in. NO1A, we're coming out. That's the wrong way around. But there's our signal. What if we go the opposite way? There's our signal. Okay. How does that compare to the original signal? We are going to need a scope probe. It's probably just a time offset, but this is insightful. This is good news. What this means is that I can use the audio I2C input module that has 2 channels, and I can mux those 2 channels into whatever I want to analyze. And then I've got the power of all of these beautiful tools. After all these weeks, it's finally wobulating. This is not that. This is different. This isn't what I wanted to wobulate. This is our testing module. So I've got this 8-channel I2S thing plugged into the Teensy4, and I've got all of my waveforms here going in as a test. What you do is you set up your pathways in this tool, and then you export your code, and you go in through the Arduino, and you start editing that code. It makes doing synthesizer stuff so easy. It's so easy. You just have this big block of patch cords, and then you tell it what waveforms you want to output from where. So my waveform 1 right now I'm defining as a sine wave of 261.63 megahertz or whatever, with an amplitude of 1. And this code is so nice and neat and easy. So we're going to hopefully be using that in order to make something that can analyze waveforms going in and out and help me work with the modular synthesizer module. So this is as milquetoast and easy and boring as they get. This is not the M303 that I'm trying to repair. But we're taking baby steps on this project. We're getting through it with little tiny steps at a time. I'm taking these tiny little steps in order to be able to get this whole thing functioning, and so we know that it's functioning. Yeah, et cetera, et cetera. So our input signal to the Max 309 is, oh, that's not the right kind of plug. Here, input signal to the Max 309 is on this second channel that I'll turn on in just a sec, and that's coming from here. And so if I turn on channel 2, is channel 4 on? What's going on? Channel 3? What is that? What is the, I guess that's the measurement channel. Whoa, what, huh? Zoom in on that. Holy crap on a stick. So that is exactly the right thing. Okay, feeling good about this. So now we need audio input with I2S. I2S. we need to look up this board that I have. Because look at that. The Max 309 is responding exactly at this frequency. There is no delay at all. And it is giving us out the exact volts that we're giving it in. That's cool as frig. That is really cool. And I'll be able to control that with 3.3 volts in order to give us our different input channels so that they'll be reconfigurable using the mux. The next piece is that I need to actually like input something. Man, this 3-volt regulator has seen better days. It's well within its own specifications, I think. God, that thing is getting hot. I don't know. That thing might blow up soon. Yeah, my scope, at least, is precise. And the Max 309 is following that voltage very nicely. And this is at audio frequencies, so it's not all that challenging for things to run at these frequencies, but it is getting us the exact volts that we want on the output. So the Max 308 and 309 are like approved for having a sense line. Like when I boot up this thing, what I want it to do is go through a sequence of testing each of the inputs, all 6 of these, at 2 voltage levels. So we'll be able to drop in, test voltage level, and go, okay, that's what these are what those voltage levels are. And we'll have to test for accuracy on that as well. But we can do that by reconfiguring this stuff and hooking up a couple of our little hookups. This is cool. This is cool. This is good progress. We're making good progress. I have 2 viewers currently on this platform. How many YouTube viewers? That one's even sadder. Where's my YouTube control? It's over here. Let's take a look at how many YouTube viewers I have. Currently, I have 3 viewers. Actually, that's pretty impressive, having 3 viewers on YouTube. That bother guy, he's going to totally pop off and become popular. We're a little too cerebral for that. We out here. We exist. We live in it. I could do a single audio input, but I don't think that would be good. I think having 2 channels means that I'll be able to display 2 charts of some kind. I could do 2 frequency analyses. I can do all that stuff. 2 1/3 viewers. You have a cat that's watching. Nice. Yeah, YouTube. I don't know if YouTube has people who accidentally leave their computers open on the page. I have friends that I know in real life that'll leave my stream up at their workplace, so they have it in like a background window with like barely any audio. I'm like, you guys don't need to do that. They're like, no, it's cool. No, I don't need your help cheating the system. But it's pretty funny. The numbers have been going down. I think that's just life, and I'll try to do some stuff to kind of get myself out there a little bit more. You YouTube viewers were the latest front in getting myself more viewers, and it's netted me a total of probably not even one hand of counting viewers, but I'm glad you guys are here. I'm glad you guys found the stream. But it didn't reach out as deeply as I thought it would. I should have maybe, well, if I go back to doing edited videos, I think I can pull in more people. That's true. That's true. Slurping lager and getting red. Yeah, people are out doing stuff. I hope they are. And those of you that have been watching my stream regularly, please go look at the sun for like 2 minutes until everything goes dark. No, wait, no, don't do that. No, I'm supposed to, no, don't do that. Just go get some fresh air every now and then. So this thing is like perfect. And actually, the test that we just did means that in the future, I'm thinking about using these for like a module. Having like a mux module where I can do weird stuff with the muxing stuff. I think that might be actually kind of a fun weirdo module for me to make for modular synthesizers. Like have it do a certain number of counts and then flip over to the next input or something. You could split out like beat assignments, halve and quarter things. Almost 400 subs though. Is that? Oh, subs on YouTube. That's actually up from the last time, because I got an email the other day, like just recently, where YouTube was like, reconnect with your subscriber, your 300 and something subscribers. So that's up to 400. I'm happy as a clam. That's very nice. Everybody's got their own advice for how I should, I don't know, like I would only listen to creators that are popular. 398, that might have been the number that was in the email. Concentrate on the hobby and what you like to do. No, listen, I know this. I've been streaming for 17, 18, 19, 20, 21, 2, 3, 7 years. I've been streaming for 7 years. This waffle that I'm saying to you guys is kind of a tired one. I've said this almost like every other stream. But I am glad you guys are here. It's really nice to be able to reach out to a new community, because it's goddamn near impossible to get people to watch from Twitch. Yeah, this many. I can't do math on stream, okay? All right, so the next thing we need to do is look up this input. Should do the knife, make a robot that does the knife hand game. There's an idea. And you just don't tell anybody that it's a fake knife, and you 3D print. I've been meaning to do this, is 3D print this. There's a 3D print that's just a finger, and if I paint it to look like a real finger, the times when I use the chop saw in the other room, I could throw the finger like at the window that leads to the other room. Or like if we do like a robotic knifey game, I can have it hold on to the finger and like drop it suddenly. Yeah, I hope this is beneficial to people, which is why I like people coming in and asking the question like, hey, how do I reverse engineer a thing? Like, that allows me to talk a little bit. CJMCU 1808. CJMCU 1808. Need a fake hand? The fake hand is good. I like the fake finger because then I can throw it. Like, I can throw it onto the desk. Like, when I use that, you guys haven't seen me do like IRL building stuff in a long time. But when I do like build stuff and use the milling machine that's behind me, you guys get a weird angle of it because this camera has to reach all the way over to there. And one thing that I do is put my bandsaw in a clamp over there. I've got a vise over there. I've never used that vise for regular vise stuff. I've always used that vise just to clamp my bandsaw onto, which is a little weird. I should make like a 80-20 adapter for it or something, or have it come out on a strut. But that bandsaw is like the most dangerous bandsaw in the world. It's like a handheld bandsaw for like cutting pipes at a construction site and stuff. But I use it as a fixed tabletop bandsaw because you can turn the speed way down on it, which is good for cutting metal. So when I hog off metal, and when I just do the initial rough cut, that'll then go onto the that'll go into the vise and get milled away. I can rough cut it by using that saw. It looks super unsafe. I have to reach and hit the trigger with one hand and then advance stuff with the other hand, and it's this big exposed blade. So I want to have something like a finger that I can throw. Dodo counter, there's a project. Yeah, it's, you know, we can come up with projects at a rate of project per minute here. That's how powerful we are. What did I spend on this thing? I don't think I spent that much on this. I think I got it off of Alibaba for way less than that. Good thing there's no information at all. Thanks for coming out on top with Google there, Amazon. Really appreciate you spreading information. Banggood, Electri Factory. Can I get information on it? That's really what I'm looking for. TI. That's for the chip itself. I want the board. I want info about the board. What is this thing? The PCM1808 device, really device, TI, who wrote this, is a high-performance, low-cost, single-chip stereo A2D converter with single-end analog voltage input. The PCM1808 device, I hate how they call it that. Just the PCM1808, you don't need device after that. Uses a Delta Sigma modulator. Bro, are you Delta Sigma? What is that even fucking... Okay, let's keep reading. Oh, doo-doo, not dodo. This isn't worth more than $8. It's just somebody put a weird price on it. I don't know why that's the first thing that came up. The PCM1808 device uses 64 times oversampling, includes a digital decimation filter. A decimation, that word used to mean a lot word, be a lot word. That's where like Russian roulette came from. You got to decimate the men, so make them play Russian roulette. High-pass filter removes the DC component of the input signal for various applications. PCM828 device supports master-slave mode and 2 data formats, serial audio input. So, I mean, technically, if I had a couple more of these boards, I could do master-slave and have more. But I think we'll just mux it. We'll mux it out. So I'll have technically the ability to measure 2 inputs. Well, wait, but that's... Hold on a second. That's not good. I either need to have this on all of the inputs. Well, unless I run gate and trigger signals, because like these need to take input or output, and I'm gonna necessarily need 2 audio channels, but then the other ones could either be output or gate input. So I'm also going to need a transistor circuit on each one. That could affect what I see from that channel. Okay, hold on. I got to think about this because I was assuming that I could do the gating and the trigger inputs, because I can do the outputs with the what is it, the D to A's. These could do like a quick little pulse, and they can do a DC level output. This would be able to measure DC level inputs. The third signal that we would have on there is a gate, like a pulse. And I would need to be able to measure pulse. So would all 6 channels need to have a 3904 switching to ground so that an input signal would show up on a digital pin, either on the port expander or on this. That could be kind of limiting. PCM828 power down, reset, 808. Okay, suitable for a wide variety of cost-sensitive consumer applications, requiring good performance and operation with a 5-volt analog supply and 3-volt digital supply. What are our limits? What am I going to blow it up? This only gets an RL unless you do master-slave stuff. Analog supply voltage is 0 to 6.5 volts. So we would need to have an MCP 6000. Well, MCP 6004 goes up to 3.3 volts, which is good for sending it into your microcontroller. But for this, I guess if we're running at 3 volts, digital input voltage, that's VDD plus 0.3. Digital supply voltage is 0 to 4. Oh, so wait, this doesn't work at 5 volts? Huh. Analog input and VREF 0 to 6.5. Oh, VCC plus 0.3, but not over 6.5. Huh, okay, so, I mean, technically I could put it through the MCP and limit it down to 3.3 volts, which is the maximum voltage of the MCP 6004. The output here, motion detected. That might be somebody picking something up, or I think somebody else came home because I heard the door close. So if I only give this guy 3 volts, that's having the amount of resolution for that signal coming in. But it could still meet all my needs because this thing is like a super duper high bit rate. This is like 16-bit or something like that. I don't need that high of a bit rate. So I could still accomplish everything that I need by having this thing on here. The only other thing is that I would need to consider how I'm going to be sensing pulses coming in on any channel, because I want any channel to do anything. Would the transistor circuit, maybe some of you guys who know this stuff a little bit better read up on this, and also we could just test it in order to get that information, but the circuit that is doing gates, which is I took out of this drawing. Yeah, I took that out of the drawing. Let's find that circuit. We'll do like mutable instruments. What is the schematics? Just any of these that'll have a gate input. So ignoring the fact that these are leading into one another, we would just have our audio input coming in through here. We have a 100 kilo ohm resistor on a 3904 that goes to ground, and then something like a 10K resistor to 3.3, and we see whether or not that affects the audio stream. We could actually do that right now. We could actually just hook that up right now and take a look at that. I definitely have those elements. So since we've got the 390, the Max 309 setup here, I can build something anywhere that just has a gate signal going to 3 volts. Although our 3 volts is pretty tortured. Maybe we'll take 3 volts over here and build that little transistor circuit. We'll just see what it does. Actually, we'll build it right here. That way my jump can be a little bit sooner. So turn this off, unplug this. This is the wonderment. This is the beauty of a breadboard, a proper test setup. It's a beautiful thing, chat. It's just a beautiful thing. It's so wonderful. We are just configurable and changeable, and this is a big device too. We're not building something that's small and unfeatureful. This is a full-bore engineering device that's going to have a lot of stuff going on. And I think I want these digital inputs to go directly into the micro, which means that I'd have 6 of them. It's not necessary to have 6 of them. I don't know. Unless I'm testing something with 10,000 triggers. And then I need a 3904 that I can put into this board, and I have one that I put on a little PCB. You can see how every stream we're doing things that are fairly simple, but we're slowly ramping it up. And the complexity is going to come from that, and we can see whether or not we're capable of operating things. I'll probably run the mux off of the port expander. If I run the mux off of the port expander, that means that I can dial in the address of what it's muxed to. The other option here is to build 6 of the MCP 6002 circuits and go into 6 of the analog inputs. And the question is whether or not we can measure those analog inputs fast enough to give us frequency measurements, to give us FFTs. Those aren't going to be totally necessary. Frequency and tone are really the ones that we want. Frequency, tone, and then the upper and lower limits of the voltages that we're seeing. Those are the important measurements that I'm going to need out of this in order to make modular synthesizer modules. Possibly like rate of trigger inputs. There's one right there. It's 3904. I need to use tweezers. So grab that. So I'll also need a 10 kilo ohm resistor. Let me put these up here. And I need a 100 kilo ohm resistor as well. I actually probably have one that I already used. Let's try to find one. Let's find a 100 k ohm resistor. I got a bunch of them, the horizontal ones. So I just need to find one of them in here. If I was better with the color codes, if they didn't all look gray to me, I would be able to figure out which one it is just by color bands. I need that thing that's like the Lego, the thing that helps you build Legos, but that's a 10K. Actually, that's the 10K. All right, there's the 10K. So 10K goes to 3 volts. So that'll go here. $10K to 3 volts, and then that goes to the collector. Ah, shit, I don't know what pin is what on this thing. So 3904 SMD. I gotta look this up. I had it memorized, and then I forgot in the past, like, 2 days. 3904 SMD pinout. So base and emitter are on the one side. Base would be the one all the way there. And then this thing hooks up in what way? I got multiple of the, okay, yeah. Oh, need this view. So it would be, oh wow, they made it even more confusing. So it's base is on the left, collector in the middle, and emitter on the right. Why is that pin cut? Weird. So actually the collector goes to 10K to 3 volts. So base is on the left. Yes, okay. Like that. And then we need to look at this. So the emitter goes to ground. Did I miss a notification? I might have. Let's go look at notifications. Where is the window that has notifications on it? It's gone. It's gone forever. I'll never see it ever again. There it is. We had a raid with a party of 1, and then Index C subscribing. I think I got that one though, and then the one before that was 5 days ago. Okay, so back to this, and we're going to hook up ground. We hook the emitter to ground. The emitter is the one all the way on the right. And in order to hook up to ground, which one do I need? I need a yellow jumper. None of these are yellow. I've got multiple of these kits, and some of them are out of particular jumpers because we've got a lot of them in use, and the Moog filter used a lot of small jumps as well. Ground I could accomplish with one of these. Well, we'll use yellow. Okay, so we'll use that. This one goes to ground. So we're just quickly building a gate signal. I can't see what I'm doing. That will determine whether or not, of course I put it in the worst spot. Oh, let's move it down. 3 volts here, 3 volts there, and then we do the resistor, like that. That goes up to 3 volts, so we pull down through the 10K, and then we put ground on the emitter, because we're pulling it down to ground. And the base is triggered by our input signal, so I need to get, I'll just do another point-to-point jumper. Where are those jumpers? What happened to those? What did I do with my jumpers? They're sitting right here. That's what they're doing. Put these resistors away. Get a jumper. Seriously? Come on. And so the base, oh, goes to a 100K. Whoops, I shouldn't have put those away. Oh no, we're still looking for a 100K. I've got some out, so I just need to find one. It shouldn't take too long to figure out which one's which. Because we do 100K to the trigger. That's 1K. What are you? Hail Mary. What's this one? $100K. There we go. So this is our input to trigger. Now we can read that in any of a variety of ways. I will choose to use my little LED thing right here, and I will run that line right to there, and we'll get a flashing LED, although it won't really be decipherable. It'll be too quick. We'll see just like a dim LED out of it, but what I can do is measure it with the scope to actually get a good readout. So this is our input, and then our output is the shared pin with the resistor. So that would be the middle pin is actually where we're outputting, and I'll just put that into any of these LEDs. We'll do the brighter green. Green should be pretty bright. And then our input is fed from, well, you need a shorter jumper than this. This is, oh wait, that's our, we'll look at that one on the scope. I don't have a place to plug in. that one on the scope, and then we'll put our signal jumping, just a shorter jumper. Those are input from the audio that we've been observing. I can't get it over there. I'll get it over here. And we'll see if that affects the audio. So turn everybody on again. Hopefully my transistor doesn't explode. Just the final doo-doo fard. There's our signal going through, and then our trigger line. Of course, at audio frequencies, it's going to be a little bit rough. You can see that it's trying to flip over, but the audio signal's too fast. Does that LED come on? No. I'll take the LED out of it. Yeah, nothing's happening on the LED. Actually, the LED to ground, right? So that should be there. Unless it's the other way around. It's too fast to see anything. So like if I take this input to the 309, oh, but that's not, okay, so we're viewing the input here on channel 2. That input goes to here and the transistor. And then on the other end of the 309, that would be output. So if I look at that output, why no output? Oh yeah, output's down here. Yeah, so those two are exactly in lockstep, right? So what happens when, what happens when I remove the 309? Or sorry, the 3904. Okay, nothing. It's not affecting our output signal. And if we observe the triggering, it's over here. Oh, that's not observing it. What am I hooking up there? Yeah, that's going with the input, and it's not affecting the input. And if we look at it doing its flipping, it should be switching a little bit. It's got just a little bit of switching going on. You can see that level's changing very rapidly, but it is changing. It doesn't have time to flip over to, well, actually, I think it is flipping to 3 volts. So it is flipping to 3 volts when it gets triggered. In the end, it's going to be flipping over much slower than that. But if we observe, well, I guess we should still observe this. And then I can take that input signal and instead connect it to plus and minus 12 volts. So if we get a very hot input here, that would be on plus 12. So that goes to 3 volts, and when it's triggered, it goes down to 0. So it's sitting at 3.3 because of that 10K going to positive voltage. And when it gets plus 12, it simply flips. And when it gets minus 12, nothing happens because it's a gate signal. It just remains at 3.3 volts, which makes it compatible with everything else. So that would work for a gate signal. We would have 6 inputs that are sitting at 3.3 volts, and if they go down to 0, then they have been triggered. And I guess what I'd need to do is give it like a button input or something like that. Okay, so that's another data point. That's another data point there. And then when audio is typically wibbling through a channel, we won't be monitoring it for gate signals, even though it will be triggering a gate signal. Okay, there's another data point. So in order to, we can do 2 channels of high quality audio analysis using the easy to use tools. And then we can put a gate signal using the 3904 in this scheme to 6 other data pins. So let's grab this. This is coming together. It's coming together pretty well. I'm pretty excited about it, actually. This is like a fully digital project, and that makes it a little bit easier. A little bit easier. You know what? Might as well just take that. Why did I cut that? I should have, whatever. So this is also going to be going to, oh my God, shift. Okay, there we go. Shift straightens it out. So that'll also go to this. And I guess instead of this, it'll go to the 3904. Not the 39, sorry, the Max 309. .308 actually, we'll use two of them. 308A and then Max 308B. So that both, you can do either channel to any of the inputs. So they'll both go to an 8-port MUX. They could go to the 4-port MUX, but then I need 4 chips in order to run all, or no, I'd still need 2 chips, so I might as well just split up L and R. I think I have a different Max chip. I wonder if that has more channels on it. What is that other Max chip? One of them's real wide and the other one's narrow. I'll have to see what I have. And this is not needed. So my inputs will be going to an individual gate trigger that'll go to a digital pin. D pin. That'll go to a D pin. And then all of them will go to their own pins on the Max 308 A and B. So that if I choose in the Max 308 to observe any of those pins, I'll be able to do that. Like any pin will be observable on left or right with I2S. So I actually need an image of the I2S thing too. The PMC whatever. Let's get an image of the circuit board. That'll do. Big enough, that should do. So let's grab that. Oh crap, I'm clicking the wrong parts of the screen. There, that. Grab this. PCM 1808. PCM 1808. Move that out of the way a little bit. Max 308 A and Max 308 B. And then this goes to the micro. I2S2. I don't think I need any of this stuff. I hope I don't need 5 volts. Although if I do, I guess I can make it, but well, I'll have to read up on how to do that for Wednesday. So a couple questions there still to answer, but we should be able to hook our microcontroller up such that it's able to drop in on any of the channels and give us a little bit of analysis. As far as this goes, I guess we're not going to be using that. I thought that, you know, it would be like gate input would have just this observation circuit on any of it, but it doesn't seem like that's going to be necessary or we're not going to, it's not going to be capable of doing that. We're not going to be able to do the analysis that we think we are directly from the analog pin, although I would like to look that up. It might just be that they decided to implement that in the Teensy Audio stuff, and it's perfectly capable of doing that kind of analysis directly from its pins. I'm not sure. I haven't done anything like that before. Let's see. Teensy 4, or I could just do art. Well, the problem is Arduino audio analysis might run into some problems with interrupts and stuff. Like if I get a library that's meant for like a regular Arduino, it might be doing weird stuff with interrupts that might collide with the Teensy 4. If I do Teensy 4 audio analysis, then we just get results for the real-time audio processing. T-Synth full kit based DIY polysynth. Arduino Teensy guitar audio shield. Teensy 4 MIDI breakout board. Teensy 36 LED music visualizer. There's all kinds of neat stuff. Yeah, they're using the audio like codecs and stuff like that. Pretty cool though. $84.99. Holy, what the hell? Making LEDs react to music is a common project undertaken by many makers. Yeah, it's a sort of a rite of passage. It often leaves you with a mess and wires sticking out of a breadboard. Yeah, but that's the whole. That's what else are you gonna do? Oh, my signals are all crazy. All right. Well, I think I'm gonna call it right now, just because I need to go deal with other stuff. And we're at a place where we're gonna start working with the 2-channel audio input. I need to do a little bit of research. I need to do just a little bit of research to make sure that this is the way to go, and not doing 6 channels into analog inputs and analyzing it from there. I suspect that this is probably a higher resolution way to go, which would benefit us, and the fact that this is taking analog in and turning it to digital, and it's an ASIC, it probably has better temperature stability, and it's probably more accurate, and it probably will get us better results. So I think I'm gonna go with this. I don't know if I have to. If I could, it would be very neat if we didn't have to involve any of this or any of this, and just have 6 channels of analog going in here, and that way we could just treat the way that it looks at those in software differently. But I just don't know if the Teensy 4, without using an external thing, would get good results. Like Teensy 4 audio without codec? No. MP3 audio library. The Teensy specific audio library. Toolkit for building streaming audio projects featuring polyphonic playback, recording, synthesis, etc. The problem is this is going to take most of my search. All of my searches are going to go through that. Teensy 4 analog input audio analysis. Audio input analog, change ADC reference voltage. And then here's the other one that's going to take all of my searches. All my searches are going to be routed into like the specific audio pin. And I wanted to see if the generic analog input pin would be able to do audio analysis, especially at the speeds that this chip runs. So I'm wondering what the exact reason Teensy 4.0 doesn't play well with a Spectrum Analyzer codec. I read a bit about the ADC not being sussed out properly, but I thought it was fixed. Saw this discussion, no Teensy V4, V5, or is it I2S supported? We use this thread as a design log. Current Teensy 4 libraries, Teensy ADC sample. Teensy 4 ADC same as above without header. Bumbler's Teensy 4 ADC library. What is that? There's more work to be done, but it seems functional, so I figured I would release what I have so far. These files are a transcription ADC library for the Teensy 4. My goal was to keep it as much of the codec from the T3 functional T4 as I could. So many of the examples from the T3 library work with little to no modification, but some things don't matter. Oh my god, this is so technical. Anyone has questions, drop here some notes. T4 has no differential pins, so if you try to use them, it'll throw a wrong pin error. What? Teensy 4 only has 12 bits of resolution. Higher selections default to 12. I think 12 bits is enough for us. I think that's fine. T4 names its ADCs 1 and 2. The code still calls them 0 to 1 to match T3. Okay, Q timer. I don't know what any of this crap is. So these are the libraries that people are updating with the new hardware. CAN bus, keypad, MIDI, Octo WS 2011, one wire, OS ping, PS2 keyboard, pulse position, quad timer tests. Huh. Radiohead. Responsive analog read. Huh. Shift PWM software serial. Yeah, what I'm looking at to see, and it's a very specific question, is whether or not we have the ability to read from the analog pins and get measurements from any of the frequencies. So if I wanted to have a 6-input oscilloscope on screen, would I be able to do that? So I need to do a little bit of research, and I don't know where to start. So that's going to be something that I got to look into. Other than that, I don't have much of a direction to go for the rest of the stream. We've built most of the stuff for the circuit. In terms of whether or not we can do 2 audio inputs into the device, and that may be all that I need, right? I probably won't need 6 channels of audio, 6 channels of control voltages and audio all at once. So, you know, I could just make the 2 channels go, and we can work with the screen from there. So mux, 2 channels, or 6 op amps going into 6 inputs, which is what I originally wanted to have happen, because then I wouldn't need to have a gate signal on all of them. But we know that our gate trigger is not affecting our audio signal in a measurable way, at least at this resolution, which is all we really need. Man, we learned a lot today. This has been a very productive day. Where's channel 1? Move channel 1 back over to the output from this. So this is going through a max 309, and it is right on target. We're talking like microseconds of delay. And then if we unflip the mux, it'll go dark. Oh, that didn't disable it. What the heck? Maybe it's so high Z that it's not going low. Technically, according to the data sheet, this should have turned it off. That's strange. Well, anyway, okay. So that'll do me for today. I'm done. Here's the end card. This one actually works this time. I'll have to edit the next later. The next stream, you have 1 day, 20 hours, 1 minute, and 17 seconds until I start up again. I will catch you guys then. There's a link to the Discord. That's where I'll be hanging out. Ben Gizmo sent me a bunch of links about using like a huge audio engine for everything. I don't want to get that complicated. I've already got parts. So I don't think I'm going to go down that path, but there's more information there if you want to check it out. Oh yeah, look at that. Finally, the voltage level. So that pin is high Z. And so what'll happen is if I give it 3 volts with no resistor to ground, right? That'll enable the 309. This is what I'm talking about with high Z. There's not a lot on that wire to dissipate voltage. So if I disconnect 3 volts, as I did just now, that is now a floating pin, but it still has 3 volts going to it. And so over time, that voltage will dissipate through the high resistance, and boom, there you go. Suddenly, it's gone. The enable is disabled on this device. Although it should probably just be a negative voltage line. I don't know what's up with that. But it probably should be a little bit more stable than that, all things considered. Oh, you know why? It's because the one went dead and the other one is just the audio going up and down. So this is our input audio, but it doesn't have like a level to trigger to. I should reverse which one's connected where. Okay, anyway. I will see you guys on Thursday. I'll be on Discord in the meantime. Have a good one, and I'll be back before you know it.